Okay, well, good morning again, everyone, and welcome back to day two. We're just going to jump right into what we need to know in order to do phase 4 of our model. So we're just going to continue building on that a little bit more today. And in this section, we're going to be primarily introducing a new object. That's going to be the main new thing, while also kind of reinforcing some of the other things we've talked about already, like using labels, port connections, and just generally working with the objects. So with the new object that we want to introduce here, the combiner object, you can sort of think of it as the companion to the separator, because where a separator's job is to take a flow item and separate it somehow to turn one flow item into many flow items, the combiner object is used as a way to join flow items together using a couple of different modes. Now, regardless of the mode that the combiner uses to bring flow items together, it has a certain set of rules that we have to follow in order to use the combiner properly. And the first rule that we need to pay attention to is how the input ports on the combiner are handled. So with the way the combiner is set up, the first input port in particular is special. The first input port to a combiner has to be reserved for either a flow item that is going to behave as a container for other flow items, or as the signal to begin collecting additional flow items. And we'll kind of see what that looks like when we kind of take a look at some of these different modes. And so really the best way to learn about how to use the combiner is to see it in action. So this slide has some important information to review, like how the combiner works, but really, showing and telling about it is really the best way. And we're going to take a look at how to use the combiner object. So I'm just going to make a new model. Default units are fine. And I'm just going to bring in a couple of sources to create some flow items. And also just a couple of queues so we can see those flow items in the model before they go to the combiner. And then we've got the combiner object. And then I'm just going to put another queue after that so we can see what comes out of the combiner when the combiner is finished with its events. I'm just going to make that a little bit bigger. Okay. So a couple of connections from the sources to the queues, nothing too fancy there. But then on my first source, I'm going to come over to the properties of the source and say that rather than creating a box, I'm going to choose a different flow item that is a flow item that knows how to behave as a container for other flow items. So I'm going to choose a pallet. There are two flow items in this list that are considered container flow items. They know how to behave as a container for additional flow items. And those are the pallet and the tote. The other flow items here, while functionally can behave as a container, they don't look very good when they do it. And it's kind of hard to conceptualize and comprehend what they're really doing if you use one of them. So if you ever need a flow item to behave as a container for additional flow items, I would recommend using the pallet. That's what we're going to choose here. We're going to see why that is in a second. So if we just run the model for a second to see what we've got, we're going to see regular box flow items accumulating in queues 2 and 3. And in Q1, we're going to see a representation of a pallet. Now, one of the most common uses of a combiner object is to provide a way to take a container flow item like a pallet and put additional flow items literally inside of it. So the combiner then in its default mode, which is called the packing mode, is going to function like a palletizer. So you can think of it that way if you want to, but really it's just providing a mechanism where you can have a flow item that knows how to behave as a container for additional flow items. So you can put things inside of something, and then wherever the pallet goes, all of the contents will always go with it. Okay. So to set up the combiner to be able to do that, the first thing we need to do is create some input ports. Now, remember, I said a second ago on the slide that input port number 1 is always reserved for the container. So that means that in order for the pallet to receive these other boxes, the pallet has to arrive to the combiner first. So I'm going to make a port connection from Q1 to the combiner, which signals to the combiner that it has to receive something from Q1 before it can receive anything from Qs 2 or 3. And then I'm just going to go ahead and make an output port to this Q4 so we can see what results out of that. Now, notice that when you make those connections and we hit reset on the model, again, notice the input port terminals where the second and third inputs are red, meaning that they are closed. The only input port that is open right now in the combiner is the first input because it won't accept any flow items from Qs 2 and 3 until it receives a pallet from Q1. So again, these are the rules that the combiner requires you to follow, is that the first input port should be the way that a container arrives to the combiner, and it doesn't allow any other components to arrive until it first receives something from that first input. Okay, everyone okay with that so far?
Yes.
Good. Now, if we click on the combiner to show its properties on the right-hand side, similar to the separator, it has all of the same functionalities as a regular processor, but then it adds a special set of options dealing with combining. So under the combiner section of the properties, we can find the configuration options, the properties that we have to modify the way combining works. So you see here, we've got the drop-down menu that lets us choose one of our combine modes. Right now, we're just going to use the default mode, which is packing. And then right below that, you'll notice that there is a table. So this is a table structure that lives on the combiner object. So it's similar to the other table structures that we've seen so far, except for the fact that it is local to the combiner object. It's not a global table. It's not a distribution table. It is a table that tells the combiner how many flow items it should receive from each of its input ports in order to complete the combining operation. Now, notice that the rows in this table say that we're going to receive from the second input port and then the third input port. The first input port is not a member of this table because the purpose of this table is to adjust the quantity of things received from these port connections. And the quantity from port 1 is always going to be 1. Or said another way, you can only pack one pallet at a time. So there's no reason to give you a row in this table that says that you're going to receive one pallet, because that's all the combiner will let you do anyway. But from here, using the target quantity column, we can adjust how many other flow items are going to be placed inside of the container. And so right now it says that our quantity is 1 from input port 2 and quantity 1 from input port 3. But if I put in another value, like let's say that I want to get 3 from port 2 and I want to get 4 from port 3, that tells the combiner to expect that many flow items. And then once it receives those flow items, it will shut its input port so it doesn't receive any more. So that means that there's going to be a total of 7 flow items placed into the container that the combiner is going to receive. Now, just to help visualize this a little bit, I'm going to go to source 2 and say during the onCreation event, I want to set the color of the flow items that leave this source such that they are always red. So on creation, set the item to red, and out of source 3, I'm going to do something similar where I say on creation, but this time we're going to say set the color to blue. So I'm just going to choose the color blue there. And so now when we hit reset and run, and again, notice that flow items are beginning to accumulate in these queues. And again, this is because the combiner has its ports closed for ports 2 and 3. It's not going to let the blue and the red boxes that the combiner wants to receive arrive until something arrives from port 1. So we're waiting on the pallet to arrive. And when the pallet does arrive, if the flow items that we need are in the queues, which they are right now, then they are immediately grabbed and placed into the pallet. And so we can see that the individual flow items are now placed inside of this container. And if we double check our combiner properties and see that we've got 3 from port 2 and 4 from port 3, that means we should see 3 red boxes, which we do, and we should see 4 blue boxes, which we do. Now, once the components are gathered by the combiner, that's when the processing time of the combiner will actually begin. And so now those flow items are being, or rather the pallet is being processed while the boxes are inside of it. And now wherever the pallet goes, the boxes just naturally follow with it because they are being carried inside of that container. Now, notice with this second pallet, if the parts that you want are not readily available in the queue, then that causes additional delay. Because if the combiner wants, 3 red boxes and there's only 2 in there, then it will wait for that one more box to arrive before it finishes collecting from that second queue. But that also is important to note that that doesn't mean that the ports are collected from sequentially. That doesn't mean that you have to collect all the things from port 2 and then all of the things from port 3. The combiner will just take them however they become available. And you can kind of see that happened with this current pallet because the arrangement of the boxes is different. Right? It's still expecting to receive something from from Q2 because at that time we only had the 2 red boxes, and so we had to wait for all 3 of them to arrive. And then with this pallet, all the blue boxes were available, but none of the red ones were, except for this one. And so that doesn't mean that the configuration of the pallet is going to be exactly the same, because we're just going to take the boxes however they become available. Whatever is available first, that's what gets packed onto the pallet. Okay, does that make sense? Anyone have any questions there at all?
Can you change that setting so that it does require a certain number from a specific source before it receives from another?
With the combiner properties, no. The combiner will always function that way. That's an assumption that we made with the way the combiner works, that you're not allowed to change. What you could do to mimic that behavior, though, would be to set up like a cascade of combiners where you have to receive from the red box or from like the red queue first before you can receive from the blue queue. So, like, for example, what I mean by that is if you were to disconnect here, and then have another combiner here. And so now we have to receive from the first combiner. Right, because now, since combiner 1 can only receive the red, oh wait, I gotta set the components list. Let's say we will still want 4 boxes there. So now that combiner 1 can only receive the red boxes, this means that we have to collect all of the red before we can move on and collect all of the blue. Does that make sense?
It does. Thanks.
Yeah. So unfortunately, with the assumptions we made about the way the combiner works, you can't make a single combiner perform this kind of action. But if you get creative with understanding the way the combiner wants to work and doing this sort of thing, you'd say, okay, let's collect all the red things, and then let's come here and collect all the blue things. Then maybe let's come to another combiner and collect all the green things, right? That can give you the results that you're looking for. You just would have to keep an eye on things like the processing times to make sure that the time it takes to actually assemble all of these components into the pallet are valid.
I have a question.
Yes.
Can we have storage inside the combiner, or will we have to mimic that with a queue right beside it?
Yeah, the combiner really can't store things. The combiner wants to only receive the things that are outlined on their components list table. So you can't have like back storage for the things that you want to pack into a pallet in the combiner. You have to have a queue object that feeds into the combiner. And it doesn't have to be a queue object either. It can be any other object. It could be a conveyor. It could be a processor. anything really at all, but you just can't store things in the combiner itself.
Got it. So you have to mimic it the other way. If create a queue or something to create that storage if we have
Correct.
a tool like that. Got it.
Yeah, because that's not what the combiner is designed to do. It's designed to collect the components that you want based on what the components list table says, but it doesn't have the ability to have like its own back storage.
Got it. Thanks.
Good. Any other thoughts or questions?
Yep.
Okay. So I think usually packing, the pack mode is usually the easiest for people to wrap their heads around because it's very visual. And it feels like something that's kind of easy to understand. You know, you have individual components, you have a container, and you need a way to put those components inside of the container. And the combiner is great at that. And that's the way that is primarily used is in this packing mode. Incidentally, too, this is where the unpack mode of the separator often comes into play, where you can pass a packed pallet to a separator, and using the unpack mode, you can take the individual components out of the container again. So that's why we didn't use unpack yesterday, because we didn't have a packed flow item. We haven't talked about that yet. But if you have a combiner that packs things together, you can later on send that packed flow item to a separator and ask it to unpack those components for you again. And that's one of the nice things about the packing mode is that it takes the individual components, puts them in the container, and all of the individual data and identity around those individual components that are in the container is all perfectly preserved because they are still individual objects. They just happen to be inside of another container. The next mode that we're going to look at follows all the same rules of the combiner that we talked about, where the input ports are special and we have the components list that tells us how many things that we want to collect. But the end result is going to look a little bit different. And so we're going to take a look at the join mode. And what the join mode says is that we're going to receive the component from Q1 first. Again, we still have to receive from Q1 first, the first input port. And then the individual components that we receive from ports 2 and 3 are going to be thought of as being merged into the thing that we receive from Q1. So in a join mode, the result that we see from the combiner is no longer a container with other objects inside of it, but it is a singular object that represents the joined or merged component. So let's see what that looks like if we hit reset and run. So again, the same rules. The flow items in queues 2 and 3 are being kept out of the combiner until we receive the thing from Q1. In this way, the thing from Q1 is representing the signal that it's okay to begin bringing together those other components. And so once we've received our pallet, those boxes get brought into the combiner. But notice now that the result is just the pallet. So in this way, think of the individual boxes as being like the individual planks of wood that make up this pallet, and that we essentially constructed a pallet out of the red and blue boxes. And the result that the combiner spits out is the pallet that we just constructed. So the pallet that we receive from Q1 is more of a representation of what is going to result from the combiner rather than something that is actually at the combiner. It's like having the work order that says build a pallet, and then the individual boxes then make up the components that it takes to build a pallet. So this is more like a material consumption, where the red and the blue boxes are consumed in order to create a pallet in the abstract sense. Any questions on that at all?
Nope.
Okay. So the last mode that we want to look at on the combiner is this batching mode. And again, all the same rules of the combiner are in play. We have to receive something from Q1 before we can do anything else. And again, the thing that is different about batching versus joining or packing is what results out of the combiner. So again, when we run this, the boxes for Qs 2 and 3 are kept out until we receive something from Q1. And then when we receive the things from Q1, We collect all of the boxes from the other input ports, but then what gets released from the combiner are all of the individual components. And the queue is kind of doing its best with arranging things just because the flow items in here are different sizes. So it looks a little bit strange, but it's working the way that we want it to. And so essentially this batching mode is saying that we want to collect a batch that consists of 3 red boxes, 4 blue boxes, and the palette now is acting as the signal that says to collect the batch. And so now the individual components again are retained, but now they are all released one by one rather than being released as part of the palette, or rather part of the palette's content. So it's collecting a batch with a specific configuration pattern where we say we want 3 of these, 4 of these, and the palette now is just the signal that says begin collecting this batch. Because if we don't receive this like signal flow item, these other flow items wouldn't be collected in the right proportions. Questions at all? Okay. So that's the big new concept here with the combiner. Additionally, in this phase, it's good to again keep in mind this label accessing idea. In particular, how I'm using the label as the send to port option, and that might merit a little bit more discussion. So I just want to show a quick little thing that simply uses some send to port stuff. So let's say that we just have something simple like a source, a queue, 2 processors, and a sink. Now remember with send to port, that by default it says that we're going to send things to the first available. Now another thing that you can do with send to port is just use numbers as a way to reference port connections. So for example, if I were to come to the send to port of the queue and just type the number 1, that means that everything is always going to get sent to the first port, and it's not going to consider anything else. So if I were to hit run right now, when my flow items come in, this is not the same as first available, right? Because port 2 will never be used in this case, because I'm saying that everything always goes to port number 1. And if I were to come back to this and say 2, hit reset and run, now everything will go to port number 2 because I said send everything to port 2. So numbers are valid inputs into the send to port field because it interprets values in this area as a port number. Now that means that I can do things like this where I use labels. And if the value of this label has potential different values, I could treat those values as possible port connections. So like if I come back to this and say, let's have a label, let's just say on creation, we're gonna set a label and a color. And I'll say that the values here can be either randomly de-uniform, either 1 or 2. And then on my queue, I can say, go to the port that is the same as item.type, because that's the name of the label that I just created on my flow item. And so now what we'll see is when we run this, the red boxes will always go to the first port because a red box is type 1. And a green box is always type 2. So here we have red over here that's type 1, green over here that's type 2. Because again, on the queue, we said that the port that you're going to use is the same as whatever your type is. Now this only works because when I set up the label the label values, I said that the values ranged from 1 to 2. Now, if I said that this was ranging from 3 to 4, so that I get blue and yellow boxes, now these flow items are never going to go anywhere because the port connection that they want to use doesn't exist. And notice that that's not giving me an error either. It's just saying, yeah, I want to send these flow items to the port that is the same as their type number. But because those ports don't exist, they just stay in the queue, hoping that those port connections will exist someday. So this sort of thing can be useful as long as you think about what port numbers you have and what label values you have, right? Because now if I come back here and say, okay, well, 3 and 4 doesn't work. So let's say that we set it back to 1 and 2. Now things begin to flow again because ports 1 and 2 exist for the things that are typed 1 and 2 for those label values. Does that make sense? Anyone have any questions there?
No.
Okay. So I'm going to give you phase 4 to start then. And in phase 4, notice that there are some significant object changes to the model where we need our sync to be moved much further downstream. And we now have queues and a combiner and a conveyor that lead up to that sync. And so what we want to have happen is that the 80% of flow items, remember the 80% of flow items that successfully leave the processor and go to the downstream that had been going to the sync, we want to send those to a queue now that represents the endpoint for non-rework parts. And then we want to be able to send those flow items to a queue that matches their part number. So that means that all of the part number 1 items, the red boxes, are going to be collected in this first queue. All the things that are part number 2 are going to be sent to the second queue, part number 3 to the third, and part number 4 to the fourth. And then we're going to have a source that produces pallets that is going to feed into the combiner. And then the combiner will want a set of boxes from each of these queues in order to pack a pallet and then release it to the conveyor and then on to the sync. Okay, so the combiner needs to be able to combine into a pallet the flow items with these part numbers 1, 2, 3, 4 in these quantities 4, 2, 3, 5. So every pallet is going to have 4 things that are part number 1, 2 things that are part number 2, 3 things that are part number 3, and 5 things that are part number 4. And since we are going to put them in individual queues, we can use the components list capability of the combiner to make sure that we choose these correct quantities out of the correct queues. And then once the processing time for the combiner is done, it can just release that flow item to the conveyor and we can watch it flow down the conveyor before reaching the sync. So the 2 big things that you're going to want to tackle here, first of all, is how do we make sure that this queue sends things to each of these queues such that all of the part numbers with the same part number value are all being sent to the same location. So this sort of thing that we just talked about by being able to put in a value for send to port and let that value be interpreted as a port number can be really useful, because if you set up the port connections just like it is here, you can say that items that have a part number label of 1 are sent to port 1. Items that have a part number label of 2 are sent to port 2, and so on and so on. And then you'll just need to configure the combiner such that it packs things from these queues in these quantities. Okay, any questions at all? All right, take a few minutes to give that a try. If you have any questions, let me know, and then we'll do a walkthrough in about 20 minutes or so. All right, so we'll move to the walkthrough then for this phase. Probably one of the things that can be the trickiest about working with this one is the number of changes that we have to make to just the layout of the model. And one of the first things that can be kind of difficult to manage are these new port connections. And I put this sort of thing into the training because it's something that comes up in real projects all the time, where you've built part of your model and you either learn something new or something wasn't the way that it was supposed to be, and then you've got to go back into a working part of the model and make changes. And being able to preserve what was working alongside the new stuff that you have to add is an exercise in just remembering how your model is set up and remembering what changes need to be made in order to make everything agree with itself. So the example of that we have in this model is what happens when we remove the connection from this processor to this sink. So when you remove a connection from an object, notice that the port connection that remains has been slotted up into the port 1 position. So by removing port number 1, port number 2 becomes port number 1. And keep in mind what that does to our send to port rule here that says that 80% of things will go to port 1 and 20% would go to a now non-existent port number 2. But if we were to add in that queue that we need to represent where the non-rework parts go and make that new port connection, now this is port number 2 because that is now the second port that was created. And this is still the first port that was created. So in order to make the logic of the processor agree with the connections that we have, we either have to change the logic. You either need to flip the percentages here so that 20% goes to port 1 or 80% goes to port 2, or you need to change the ports to agree with the logic. And in this case, I feel like changing the port connections is a little bit easier because we can go to the port section, say that we want to view our output ports, and then I'm going to put Q2 ranked ahead of Q1 so that it's now on the first output port. And that'll mean that all of my good non-rework parts now will come into Q2 instead of going to the sink. So I'm just going to move the sink way downstream, and we're going to add in some other objects. So I'm going to have a source that will create palettes for me. I'm going to have a queue for all the things that are port number 1. I'm going to use my double click menu just because it's a little bit faster. So there's my queue for part number 2. There's my queue for part number 3. And a queue for part number 4. And then my combiner. And then I'm just going to drag out a conveyor. And this is the first time we've seen the conveyor, but we'll spend a lot more time with the conveyor later on. I think tomorrow we'll spend a lot of time dealing with conveyor behavior and stuff like that. But for right now, we're just introducing it in a really simple way. And now I need to make my connections to allow the flow items to go where they want to go. And I just want to show you guys here that there is a nice little shortcut that you can use for creating port connections to a lot of objects all at once. And this is using a mechanism that we call the selected object. And you can create selected objects by holding down the Shift key and dragging a lasso around your objects. And that highlights them all in red. And the selected objects lets you do some pretty cool things like for batch editing a group of objects. But one way that we can work with a group of objects like this is to make a port connection from one object to a member of this selected set, and it makes connections to all of them. So that's kind of a nice thing, saves a little bit of time. And we can do the same thing when we make the connections to the combiner. If I control click on the source to add it as part of the selected set, and then make a connection from one of them, it makes a connection from all of them into the combiner. Now, one thing that you have to watch out with this, though, is that the connections are attached to the combiner in the order that the objects were created. So because I created my source first, it's the first input onto the combiner. But if you created the queues first and then the source after that, then the source might be like the third or fourth port on the combiner instead of the first one. But again, just keep in mind that if the port connections are not arranged the way that you want, especially when it comes to the combiner, because the port connections on the combiner are very important, come to your port properties go to your input ports and make sure that the sequencing of the ports and the objects makes sense for how you want to use them. So in this case, I just want to make sure that my source is the first input into the combiner. Okay, and then to turn off the selected set of objects, I just shift click in an empty grid space, and that red selection goes away. And then from the combiner, I just need to connect to my conveyor. And then from the conveyor to the second. And then on my combiner object, actually, before we do that, I'll go back to Q2. I need to change some properties here. So Q2 says that we need to send to the port that is the same as the item's part number label. So all part number ones go to the first port, all part number twos to the second port, because those are the values that we have in the part number label. We have values 1, 2, 3, 4. And then on the source, I want to make sure that my flow item class is producing one of my containers. So we're going to choose a pallet. The inter-arrival time, like I mentioned earlier, the inter-arrival time doesn't really matter for how often a pallet gets created. One thing that you could do, though, is if you put in an arrival time of 0, this is sometimes a handy trick that you can pull with the source object, where if you say inter-arrival time is 0, that means that whenever there is downstream availability, a pallet will be released to that object. And so a 0 time here means 0 time between pallet creations, which is a way of assuming infinite supply of pallets. We're never going to wait for pallets to be created with an inter-arrival time of 0. So as soon as the combiner finishes packing a pallet, a new pallet will be immediately delivered. A new empty pallet will be immediately delivered to the combiner. But like I said, it doesn't really matter for this one. You'd almost get that same effect anyway with the default, just because of the arrival rate of the components being what they are. You'd almost never have to wait for a pallet to be delivered anyway. But this is a way to make sure that, you know, the delivery of pallets isn't going to be a bottleneck in the model, just by saying there's always a pallet available whenever we want one with an inter-arrival time of 0. Okay, and then on the combiner, I just need to set my components list table such that we receive the right quantities from each of my ports. So we want 4 from the second port, which represents my part number ones. We want 2 from the third port, 3 from the, 3 from the fourth port, and then 5 from the fifth port. And then when we hit reset and run. So the model starts with a pallet in the combiner all ready to go because of our inter-arrival rate of 0, where there's always a pallet available. And so now we're just waiting for boxes to come down. And notice how they're passing through the queues and getting put directly onto the combiner, or rather the pallet in the combiner, because the pallet is there waiting to receive the boxes as they arrive. And then once the contents that we want all arrive, then the pallet will be released and it will go shooting down the conveyor because of the conveyor speed. But if we slow it down a little bit, when the final boxes are being collected, we're looking for another yellow box, it looks like, another couple of yellow boxes. And then you can see the completed pallet with all the configured parts that we want. Then if we just speed this up and let it run on for a while, you can start to see generally how the model's behaving, where we have a reasonable supply of things in Q1 as we put them downstream as they wait to be brought into the combiner. And again, notice how pallets are always available because of that inter-arrival rate of 0, which was something, again, you didn't have to do, but for this model, it potentially makes a degree of sense just to say, well, let's assume that we always have a pallet ready to go. We're never waiting for pallets to show up. Okay, any questions on that model? Okay. So now we've got a model that is built, and we've used this as a way to learn a lot about the way the objects work, and like just building a model, generally speaking, in FlexSim is kind of using the objects, using the different properties of the objects to get the behavior that we want. And now that we have a model, now we can start talking about analysis. We can start saying, okay, even though we've got some reasonably, nice looking like outputs over here on the dashboard window, how can we actually use this model as a tool to learn something about our process? And that's what we're going to learn in this next section, where we are going to talk about experimentation and how we can use the model as an experimenting tool, where we can learn how the effect of changing different input parameters to our model will have an effect on performance measures that we're interested in learning about. And so we're going to talk about a lot of tools here that will support the creation and execution of experiments, primarily things like our input table, like the model parameter tables. We'll take a look at performance measure tables as a way to aggregate our outputs of interest. And we'll also talk about some features of the software that allow us to put our model into a good position to more easily conduct experiments. And so we'll take a look at what we call object groups and dispatchers as a way to support the creation and the execution of experiments. Okay, so the first thing that I want to show you here is that we're going to change the model layout a little bit. So you'll notice that there is a new object in here that's called a dispatcher. And the dispatcher object has a lot of potential uses, both within the context of experimenting and also outside the context of experimenting. So we want to learn a little bit about dispatchers for a minute, because we're going to use it in this model to support our experiments. Now, the typical use of a dispatcher is to help us coordinate the behavior of a team of task executor objects, like a group of operators, or a group of travelers, or AGVs, or forklift trucks, or something along those lines. Because what a dispatcher allows you to do is it allows you to send requests for task executor objects into a central location, the dispatcher, and then allow the dispatcher to send those requests out to the members of the team. So in that way, the dispatcher becomes like a common pool of work that needs to be accomplished by the task executors. All the requests for the operators would come into the dispatcher, and then the dispatcher uses what's called pass-to logic as a way to send those requests out to members of the team based on different criteria that you can set. So in a lot of models, you might use the dispatcher purely for that organizational feature, where you might say, well, I've got 4 people who are all doing the same jobs. And so rather than trying to send those jobs individually to the team members, I'm going to send those jobs into the dispatcher and let the dispatcher figure out how to dispatch those jobs out to the team members. So the way that you use a dispatcher would be, first of all, to change, in this model, some of our port connections. So I'm going to go to my operator, and I'm going to go to the port properties, and I'm going to look at my center ports, and I'm going to remove these connections from my operator, because those connections were allowing the queue and the processor to send work requests into the operator directly. But if you want to use a dispatcher, what you would do instead is say that those center port connections go from the queue to the dispatcher and from the processor to the dispatcher. So now the requests for doing things like transportation and being involved in setup times are coming to the dispatcher. But the dispatcher doesn't have the ability to actually execute any of these tasks. And instead, what we need to do is say that we are going to send those requests out to the operator using an A connection. So the connection pattern for using a dispatcher is pretty specific. You have center ports that come into the dispatcher from the requesting objects that need a task executor to be involved. Then you have output ports from the dispatcher to the team members to represent the idea that those job requests are being sent out to the members of the team. Okay, everyone okay with that so far?
Yep.
Okay, so with this minor change to the model, if you hit reset and run, it doesn't appear to run any differently, right? Because the only thing that we've done is we've added another layer of control where the requests to do various jobs in the model are being sent to the dispatcher and are now being sent to the operator. Right, so not too different from what we saw before. But the nice thing now about the dispatcher is to say, well, what if I wanted to see what happened if we added a second operator? What if we added another operator to this model? And I want her to be able to do the same things that my first guy was doing. Well, now all I have to do to incorporate her into this workflow, is to make an output port to the second operator. And now if there's enough work for both of them to be engaged in, the dispatcher will request both of them to be involved. So now there's enough work for both these operators to do, so both operators are now in use. I didn't have to change anything else about the model because the dispatcher knows how to coordinate between the two operators. And so if there's nothing to do, they're both going to be idle, but as soon as more things begin to arrive, they will both be involved in the different processes that we need the operators to be involved in. Now, adding a dispatcher to a model like this is something you can do in any model for any reason at all. Anytime that there is like a shared queue of requests that you need task executors to all be able to pull from. You could have multiple dispatchers in the same model to represent the control point for various teams in your model. But again, another nice thing that the dispatcher allows us to do is it allows us to support experimentation, where we want to see the effect on our model outputs by automatically adding additional team members to a team associated with a dispatcher. And we're going to see that when we jump into discussing some of the other features that support experiments, and you can see how we're able to do that. Now, another organizational feature of the software that has uses both inside and outside of experimentation is the notion of formalized object groups. An object group is useful for adding some structure and some organization to your model, where you can create in an addressable group of objects that have something in common in some way. Sometimes we create object groups to make it easier to create aggregate statistics about a collection of objects rather than showing the statistics about each object individually. Sometimes you might create groups of objects to make it easier to edit and update the properties of a set of objects all at once. And there's some other things that we'll see later on in the week too that groups might be useful for. And again, another useful way that we can use a group is to support experimentation, where maybe you want to see the effects of adding multiple objects to a group and see what effect that might have on your model. So just to, again, kind of support where we're going in terms of experiments, I'm going to come to the processor, and we're going to make a group out of this object. It's a little bit weird to create a group out of a single object, but as we see in a little bit, it's going to make a little bit more sense. So if you right-click on an object, you get the option to add that object to a group. Now you'll notice that there are some groups already in the model. There are a few places where we will create groups of objects for you automatically to make it easier to work with and address those objects. But you can also add your own customized groups that have whatever meaning you need them to have. So this processor then, since I right-clicked on the processor and I go to object groups, I'm going to say that I want to add that to a new group. And so right now, the only member of this group is processor 1. And then I'm going to rename this group the processing group. Now, as far as naming groups go, again, you can really name them whatever you want. But I use a convention in my groups where I always include the word group in my group names, just to clarify that I'm referring to a group of objects in this case, rather than like a single object. That's mostly for my own clarification and readability on the model. But I would encourage you think about what kinds of naming rules you want to set for yourself and what makes sense for the way you think about things, and so that your models make better sense to you. But this is something that I've started doing just because it makes certain things easier for me, but it's not required. Okay, so we're going to put that aside for now. And I'm going to remove my other operator for a second. And the next thing that we want to spend some time talking about, again, to help support this notion of conducting experiments on our model, is what we call the parameter table. Now, the parameter table is a new feature. This has only been in the software since January of this year. And the reason why it exists now is because we're trying to help our users develop a workflow, not only for building a model, but also for conducting experiments. And so this parameter table represents a pretty significant departure away from the way that we used to do things like this in the past, where we kind of left it up to the user to figure out what parameters were important to your model and how you were going to change them and how you're going to access them. We kind of just said, use the global table and do whatever you want. Just kind of said, you figure it out. And so the parameter table represents an attempt by us to begin to more formalize the process of defining good inputs to your model that are easy to change. Because one of the things that can be sometimes difficult about working with a FlexSim model is that there's so many different properties that you can change that you have to remember what object property is doing what. And if there's only certain properties that you're really concerned with, it can be difficult to go around changing them, not just for, like informal experimentation, but also formal experimentation. Like if you just want to say, well, I want to see what happens really quickly if I try this, like adding in a second operator, manually can be a few steps, or changing an object's processing time can be a few steps. But if you can create a central location where important model parameters are located, that makes it easier to access those parameters and easier to change those values in order to see what effect those values may have on your model. And so the idea behind the parameter table is to create for you that central location where you can say, here are the parameters of interest to my model, and here are the possible values that they could have. And this gives me a simple interface that I can use to change those parameter values rather than having to go out to the objects and change their properties directly. You can use this table interface to do it instead. So because the parameter table is a table, it allows us to, again, create that central location, which is one of the nice things about tables in general, is that it gives you a place where you can organize important model data in a single location, which is one of the reasons why we use tables in a model anyway. And so the parameters table gives us a way to formally define what a parameter to your model is going to be, what kinds of possible values it can have, how those values potentially could change, and provides an easy way for the experimentation feature of the software to update those model parameters for you automatically. So let me show you an example of setting up a parameter. And this slide is like a synopsis of the parameters table section of the manual. So if you wanted to refer to the manual or to the slide for additional information about parameter tables, that's great. But I'm just going to try to do a more of a practical demonstration of why you might, or how and why you might set up a parameter table. So in our model right now, there is already a parameter table. So in the toolbox, you should see this model parameter tables, and it says parameters. And if you double click on this, it just opens a little window. Now for me, it opened up over here because this is where I had my global table, and it just attached itself to that same panel. So it's just a different tab on this little table area that I've set up. But for you, it might open up on like the main panel of the screen. And if you click and drag on the tab of that window, you can reposition it someplace else on your FlexSim interface. Now, parameters have a name that is defined by you as the modeler. By default, a parameter just says like parameter 1. If I add another row to this parameter table, it says parameter 2. But I'm going to say that I'm going to create a parameter that I'm going to call my team size. And in the description column, I'm going to describe this as a parameter for easily updating the number of TEs or task executors associated with my dispatcher 1. Okay, so I typed a lot in there. And the description column is really there for documentation purposes. So if I'm naming my parameter team size, and I'm saying that the purpose of this parameter is a way for me to automatically adjust the number of operators associated with my dispatcher, this is there mostly to tell me what I'm thinking with this parameter. It's not required. You don't have to fill in the description. You don't even have to fill in the name. But I would consider them really good practices to use because, again, they help with your documentation, not only for yourself, but also for anyone else who might be looking at your model. So that if they come to your parameter table and say, oh, he wants to be able to change how many task executors there are associated with dispatcher 1, okay? Now, the name and the description are completely in your hands. The display units also is completely in your hands. In fact, what I'm going to do here is I'm going to say this is my display unit is members. And so if you read this, it says that the team size right now has a value of 1 member. And what I would like to be able to do is if I change the value, I would like that to automatically increase the number of members associated with my dispatcher. And so that's what the value column of the parameter table is for. It's to give us a mechanism where if we were to change this value, it automatically changes something about the model. Maybe it's going to change the number of team members. Maybe it's going to change our processing time. Maybe it's going to change the maximum capacity of a queue. Maybe it's going to change the arrival rate of flow items. It could really be anything. Just about anything that you can change about the model can be used as a parameter to the model so that you can have this location where you can easily adjust parameters without having to find the object and the property that you want. You can just change it here in the table, and that would automatically take some effect in your model. Okay, is that making sense so far?
Yeah.
Okay, so how do I associate this value with the number of task executors associated with my dispatcher? So if you click on the value, you get this drop-down triangle where you can see the properties or the configuration options that you have for this parameter. Now, one of the first important configuration things you need to choose about the parameter is defining the type of parameter. And the type of parameter is telling you what kind of value this parameter represents. The default value of a continuous would mean that it could be any real number between the lower bound and the upper bound. So a continuous parameter with an upper bound or a lower bound of 1 and an upper bound of 10 would mean that any real number between 1 and 10 is a valid value of this parameter. Now, because you can't have fractions of an operator, continuous doesn't actually make any sense in this case because the number of team members associated with my dispatcher is not a continuous value. It's not a real number. It would be more appropriate to describe this kind of a parameter as an integer because you can only have discrete numbers of operators. You can have 1, 2, 3, 4, 5, whatever. And so an integer parameter type with a lower bound of 1, upper bound of 10 just means you can have any integer value between 1 and 10. So this would now mean that I potentially could have anywhere between 1 and 10 team members. But still, right now, this is just a value. So how do I make this value from 1 to 10 correspond with the number of operators on my dispatcher? Well, this is where you might potentially use the reference field on the parameter. The reference field means that we want to associate this value with some object in the model. So if I use my eyedropper and come over to the dispatcher, this gives me a couple of options. It either lets me just reference the dispatcher, and then it's up to me to define what that reference means later on, or I can use one of these options that we have that says delete and copy out objects. So delete and copy out objects means that if I change the value of the parameter, the dispatcher will automatically either delete or copy members of its team in order to arrive at the team size defined by the upper and lower bound. So if I choose delete and copy out objects there, if I say 1, that means I'm only going to have 1 operator. But now if I come in here and say, let's have 3 operators, and then hit reset on my model, watch the dispatcher when I do this, it automatically added 2 more team members to the dispatcher. And I can see them represented by their output ports. And so if I move the objects, I can see the individuals. So now I have operator 1, that's my original operator. Operator 1_2, that's a copy of operator 1. And operator 1_3 is another copy of operator 1. So now I can set the number of my team size to whatever value is in this parameter. If I said 10, which is my upper bound, now I have 10 team members. And if I go to the dispatcher, go to the ports, go to the output ports, I can see that we have operator 1 all the way through operator 1_10, so that I have all 10 of my operators defined by the parameter. Now, if I were to try to set my team size outside of my bounds, if I said that I want 12 operators, it's actually going to give me an error. And it says, hey, you said that the maximum size of the team was 10, so I'm not going to let you set it to 12, because my upper bound says that 10 is my maximum and 1 is my minimum. Now, the upper and lower bound portion of this can sometimes feel a little bit like, well, why do we need this? And it really has to do with another feature of the software that we're not going to get into this week called optimization, where when you're defining an optimization algorithm, you have to establish an upper and lower bound for possible variable values. So the optimizing algorithm knows what values are potentially valid, so it doesn't just try infinite values, right? And so that's what the upper and lower bound is there to support. It supports optimization, but it's part of the parameter as a whole, because the optimization feature and the experimentation feature are also very closely related. So when setting up a parameter to your model, whether for experimentation or for optimization, we want you to go ahead and establish that upper and lower bound, some kind of a constraint on the parameter to establish the rules of what that parameter could potentially be. Okay, so now if I, again, like go back to something like 2, hit reset, it takes me back down to 2 members of a team instead of 1. So one of the nice things about this, not only for experimentation, but also just in the regular workflow of the model, where when I wanted to have that second operator before, I had to drag out the other object, manually make the connection. But now that I've set up my parameter, I can adjust the size of the team to any amount that I want just by typing in a value into my parameter table. And so we want you to use the parameter table as a way to identify inputs of interest to your model, to make it easier to adjust those inputs, not only in the formal experimentation, which is what we're leading our way towards now, but also for just constructing your model and seeing what parameters of interest will do if you change them. Because it's really easy to change these table values and see what happens in your model if you make those changes. Okay, any questions so far? Okay. So let's go ahead and take a 15-minute break. Let some of this settle in a little bit. And then when we come back, we're going to talk about another table structure that supports experimentation called the performance measure table. And then we'll get into constructing an experiment and actually seeing how experimentation works with our model. So as we continue talking about some of the features of the software to support experimentation, another one we want to talk about really quickly is performance measures. Now, there are a lot of different ways in FlexSim to display outputs of interest and get a feel for how your model is behaving using these output reports that we generate. We've seen some of that already with the dashboards, and the performance measure table is a way to create aggregated reports from outputs of interest in the course of doing an experiment. There's really not a ton of use for performance measures outside of experimentation, but again, it's something that is set up outside of experimentation just to have it available as part of your regular model workflow if you choose to. But again, its primary use is to support the creation of output reports at the end of an experiment. So to set up a performance measure table, we would come back to our model. And again, there's already a performance measure table in your toolbox, at least there should be already. And if we double click on that, that opens up as another tab on your tables, where now we have a performance measure row, a value that's being reported, and also the display units and the description. And so very similar to the parameters table, the performance measure name is up to you, the display unit is up to you, and the description is up to you. Now, like, let's say, for example, I wanted my throughput by type. Well, actually, we'll just do throughput. If I want something like my throughput to be in my performance measures that my experiment is going to be aware of, then I can say that this is going to be my total throughput. And then my display units is going to be pallets, because that's what, my throughput chart is actually measuring now. Is it's measuring created pallets or completed pallets as they get to the sink, because this is the throughput directed at the sink object. Then if you want to fill in your description, you can. I'm not going to do it though this time. And then on your value, we configure the value in a similar way that we do with the parameters. Notice though that the only field that we really need to worry about here is the reference field, because we need to direct the performance measure to some stats gathering mechanism in the software, be it a stats collector object or a dashboard chart or an object statistic. So if I use my eyedropper here and go to my chart, it's going to say, okay, what do you want to have in your performance measure? Do you want to measure the input or the output? And then for those choices that we're getting, we can say, well, do you want the input average? Do you want the input sum, the minimum, the maximum? And so if you choose something like input average, that's going to be the average input over the course of your experiment. So right now it says that its value is 0, but if I hit reset and run, we're going to see that the performance measure value will update when the chart does. So as we finally create our first palette, we can see now that the chart says that our input is 1, and now our total throughput says that we have created 3 pallets. So I would say that performance measures are not meant to replace dashboards, but they're meant to supplement and improve them, because it allows us to choose these outputs as part of my performance measure set. And as we'll see in a little bit, the experimenting feature of the software allows us to do some cool things with these performance measure values. But right now, we're just going to do that. Okay, any questions so far? Okay. So in phase 5, what we're going to do is we are going to construct an experiment and talk about experimentation along the way. So this phase is going to be a little bit different. Rather than having you guys go off and do this on your own, I feel like it makes more sense to do it together. So we're going to use this as an opportunity to gain some more experience using our parameter tables, our performance measure tables, and we're going to conduct an experiment where we want to experiment with the number of processors to find what is the quote unquote best number of processor objects. And we're going to do the same thing with operators. We want to know what is the best number of operators for our model, and we want to see the effect of reducing our processor's rework rate for anywhere between 20% to 5%. And we want to see what effect that has on our model. And the main question that we're trying to answer here is we want to figure out where our model's bottleneck appears to be. So kind of what I'm assuming here is that if we have more processors, more operators, or a lower rework rate, that should increase our throughput. And so we want our experiment to either prove our hypothesis that these are the primary inputs that have an effect on throughput. And if it's not, we want to see if the experiment can help us to find where our bottleneck actually is. In order to use the experiment, a little bit of background on what experimentation does. So what experimentation is trying to help us do is it's trying to help us automate the workflow of changing model parameters and seeing their effect on our model outputs. So this is why we have the parameters table and the performance measure table, where we want to kind of formalize, these are the inputs of interest and these are the outputs of interest. And what happens if I change my inputs? What effect is that going to have on my outputs? And so rather than doing this process manually, the experimenter allows us to automate this by being able to say, here are the input parameters that you're allowed to have. And now I want you to run the model automatically a whole bunch of times and then tell me how the model behaved. Now, this is really important because a single execution of a model is not very helpful in terms of analysis. It doesn't really tell us very much about how the model behaves generally, because a single iteration of your model is only giving you results based on a single set of random numbers. And we don't know if the results that it generates are near the mean or far away from the mean or represent like an outlier. A single run of the model just doesn't tell us very much. And so what the experimenter allows us to do is it allows us to run a lot of iterations of our model really, really quickly so that we can compare the results of all these different iterations and see how the model behaves in a more general sense. And the other nice thing that it does is it automatically creates these aggregated output reports so that we can more easily compare those results against each other. And it will also tell us things like what's the average of your performance measure, what's the minimum, the maximum, the median value, you know, all information that would be helpful for analyzing the outputs of interest. And this is why, you know, creating, you know, having a good understanding of model inputs and outputs, like we talked about yesterday, is really important because we want to have a good grasp of what inputs have a greater impact on our model versus others. And we want to be able to include those in our parameters tables so that when we experiment with those, we can see the effect that they have on our model. Okay, so that's experimentation in a nutshell. It is going to automate some of our workflow for us, so we don't have to do a lot of clicking on our own. We can set up an experiment and then just let the experiment run. And then when we come back later, the results should all be there for us. Okay. Now, when using the experimenting feature, there's a little bit of vocabulary to be aware of. The first important bit of vocabulary for experimentation is this notion of a replication. So when we say replication in the context of experimentation, we're saying that we're running the model one time. We're running a version of our model with a set of inputs, and we want to see the results of that single replication. And like I said, a single replication of the model or a single run of the model really doesn't tell us very much. And so the experimenter's job is to run many replications automatically and create reports about how our outputs of interest performed during those replications. Now, a scenario is defined as a set of replications where parameters will be set consistently for all the replications of that scenario. And so you might have a scenario where you have one team member associated with your dispatcher. You might have another scenario where you have two team members associated with your dispatcher. And so the job of a scenario then is to define a set of inputs that will be consistent for a set of replications. And then again, the experimenter will create reports that allows you to say, this is how scenario 1 behaved, this is how scenario 2 behaved, and this is how scenario 3 behaved, where you can change all these different parameters for a set of scenarios and more easily make comparisons between those scenarios. When setting up an experiment, there are two time-based properties that we have to set. The most important one is the end time, where we are basically defining the duration for a single replication. Most models, when they get designed, they're a lot like the model that we have in that we've been building so far, where it could potentially just run for infinity amount of time, right? If we come back to this model we could hit run on this, and there's never a time when this model would stop. We could amp up the run speed all the way to the maximum, and there's never a natural moment when this model would ever stop. So when you're running an experiment, we need to define a time period where statistics that we gather actually matter. And so the end time allows us to say that a single replication of our model runs from time 0 until time whatever makes sense for you as a modeler. So when you're defining your end time, it's going to be kind of dictated to you a little bit by your model, where you will need to figure out like what is a proper duration. Is a duration like one day, like 1 24-hour period? Is it 1 8-hour shift? Is it a week? I've seen some models where a single replication is actually a year, but it's going to be kind of up to you to figure that out as the modeler, to decide what is the proper amount of time to say that from time 0 until time X, that is a statistically useful segment of time that I can use to analyze my model. Okay, now kind of closely related to that is the idea of a warm-up time. The warm-up time property of an experiment is a way to define a period in the model from the beginning of the model to the end of a warm-up time where statistics that are gathered don't count towards your performance measures. And that might sound kind of weird. You might be thinking to yourself right now, well, why would I ever want to exclude some of my output data from my reports? Well, because sometimes when you have a model, the beginning of a model might represent an unnatural, impossible state, right? Like if you come back to our model, right? When you hit reset on a model, there are no flow items anywhere in the model. There is no work in progress. There's no holdover from like a previous day or a previous shift. The entire model starts completely empty and all of the resources are available to be used. In some models, that might represent a very unnatural state. This might be something that can never happen because maybe like you have an assembly line that runs 24 hours, or you have a hospital that always has patients in the emergency department. Any kind of a situation where the beginning of the model, where it starts empty and all resources are available, if this is an unnatural state of being, if this is not something that can ever actually happen, then you may want to use the warm-up time to allow you to exclude any stats that are gathered during that unnatural state so that they don't produce any weird outliers or skew your results, right? And so warm-up time allows you to let the model run for a duration of time and put itself into a more natural state, and then only gather stats after that point. So again, the decision of whether or not to use a warm-up time is going to be up to you. It'll be partially dictated to you by what kind of model you're building. If it's a model where the model never starts empty with no work in progress, then you're probably not going to want to skip over the warm-up time. You're probably going to want to include warm-up time in your experimentation. But if your model is like a retail environment, where doors open at 10 and the doors close at 10 at night, then you probably don't want a warm-up time because that's a natural state where the doors open and all the resources are available. There's no customers in there or anything like that. So you want to capture that data as part of your output set because that represents something that could actually exist. So again, it kind of depends on you. It depends on the model, depends on what kind of model you're building. So whether or not you use a warm-up time, just remember what it does so you can decide, is this a situation where I should include a warm-up time, or is this time where I don't need a warm-up time? Does that make sense? Anyone have any questions on any of that? Okay, so a couple of notes to think about when getting ready to conduct an experiment. And it's also kind of helping us define a bit of a workflow for when you want to begin doing experimentation. The first thing to do before you run an experiment is kind of informally experiment with your model a little bit, where you run your model for a while, observe to make sure that it is behaving in expected ways, that the results that you're getting are reasonable, without doing really hardcore analysis where you just want to say, okay, these values seem somewhat reasonable for the model. This kind of makes sense. It's behaving the way that we expect it to. Logically, it's acting the way that we would expect. And just keep an eye out for any potential problems or weird outliers or glaring errors in your model, because you don't want to experiment with a model that has any hidden time bombs in it, because that can really skew your results, and it's hard to figure out where those bad results are coming from. So you might do something simple like just keep an eye on a couple of outputs of interest on like your dashboards and just say, okay, things seem to be working along okay. Then right about here, we start getting a lot of content, and maybe this represents something that we need to pay attention to. Maybe this is something that's like, well, this is unexpected. I don't know why all of a sudden we're getting this buildup of content. So what's going on in the model that's causing this? Is this something expected? Is this something unexpected? Is this within the realm of possibility? Does it mean that we've created a problem in our model? Is something broken? And just generally try to verify your model to make sure that the results are at least somewhat reasonable. It's basically just debugging your model and making sure that things work the way that you expect. And hopefully by that point too, you've also kind of decided on some performance measures that you feel are reflective of your model's purpose. You know, like I said yesterday, we spent a lot of time talking about this idea of identifying outputs of interest and trying to figure out what the outputs are going to be that you're going to use to measure the behavior of your model. Hopefully you've decided on a couple before you start building your model, but you may also encounter new ideas over the course of building the model where you might say, oh, you know, I learned something while I was building this, and it might be useful to use this as an output in my experiments. Because you can add outputs anytime that you want. It's good to just kind of keep an open mind about what outputs of interest are going to be important to your experiment. And if you haven't already by this point, it's a good idea to create a dashboard or some kind of a stats gathering mechanism that will gather the information needed to report on whatever performance measure you've selected. The dashboard charts are a great first line of defense for that, where you can choose the outputs of interest that you want. And hopefully around this time too, you've also started to consider the input variables of interest so that you can say, okay, these are the things that I want to be able to experiment with. I want to see what happens if I change this and what effect that's going to have on this. Right. So let's do that right now. Let's add another performance measure to our model. We've already added total throughput. That's just going to count the total number of pallets created. But I'm going to create another one here. Actually, got a little something screwy with my UI here. Let me open default workspace and just reload it. So I'm going to go to my dashboard, and I'm going to choose an output-based statistic again. And this time I'm going to choose output per hour. And we're going to look at this as a bar chart. And so essentially what I want.
Adding these to our models as well, or are we just watching you?
If you want to follow along, I think that'd be helpful.
Okay.
Yeah, but at least it's also in the recording if you want to go back to it later. But it'd be good to add this stuff in too. So with this output per hour chart, what I'm looking for is the creation rate of my pallets. So I'm already measuring in my performance measures the total number of pallets created. But now I'm also going to see how many pallets I'm creating per hour. So just kind of setting up my UI. And so the object that I want to measure my stats from again is the sink. And I want my interval, I want to measure that per hour. So that sets up the dashboard, but then I also want to add this dashboard to the performance measures table for my experimentation. So I'm going to call this pallets per hour. And again, my display unit is pallets. And this time my my reference is going to look at this chart. Oh, and I have to hit reset before I can do that. And I want to get the average throughput. And again, if we just run the model, we can see what that looks like. Right, so we hit a point like where I just let it run for a really long time. And we've output 111 pallets for a rate of 6.29 pallets per hour. Okay, is everyone okay with that so far?
Hey Regan, if you don't mind, show that value again, how you set the value.
Yeah, so on the drop down, I just used the eyedropper on the reference field and I directed it at this output per hour. And that's the throughput average.
Okay.
Okay, now we said earlier too that we wanted to define some parameters. So since we're at this stage where we're adding an output of interest, let's also set up the other variables of interest. And so we want to have a variable that allows us to adjust the number of operators. And we already have that. We did that as the example with the dispatcher, but we also want a parameter that allows us to adjust the number of processors and also a way to reduce the rework rate. So if I open up my parameters table again, I've already got my team size parameter. So I'm going to add another one. And this one I'm going to call number of machines. Because I want this to adjust the number of processors that I have. And my display unit this time will be just machines. And then I need to set up the variable. And so similar to what I did before with the variable that looks at the dispatcher, I need a little bit more room here. I need to choose the type. And so since what we're talking about is the number of machines, this would make sense to be an integer again, because I need a discrete number of machines. And then for my upper bound, my lower bound, I'll just leave it at 1 through 10. And then for my reference, instead of referencing the processor though, I am going to come to my group that I created and say that I want to delete and copy group members so that when I change my parameter value, it will automatically create or remove processors from my model. Okay, so I'm going to choose that option. And if I test this out, like if I come back to my number of machines and put in 2 and hit reset, now if I move processor 1 out of the way, you can see that there is now another processor, and it mimics all of the port connections that the original processor had. So now with this variable, I can automatically have between 1 and 10 of those processors. Now, one thing that you'll notice though, is that we didn't make any assumptions about where physically those processors should be placed. So the parameter table assumes then that they should just occupy the same XYZ location. Now that's something that you can change. If you wanted to go into the code for the onset trigger, you could assign the created objects new locations in the model automatically. But we didn't do that automatically because we didn't want to assume how to place the newly created objects. But if that's something that you wanted to do, you could do it if you came into the code and adjusted where those objects are placed, because by default, they just get placed at the same XYZ coordinate as the original.
Hey, Regan, could you explain the difference between the process group and the process, or like the processor instead? So like why you pick processing group instead of just the processor itself?
Yeah, because if you use the if you use the eyedropper for the reference on the processor, it thinks that you want to copy the output object. So what it would do is it would mimic its output ports and it would create more of these queues.
Okay.
But if we direct it to the group, then it adds or removes members to the group. It doesn't clone itself, it clones objects that it connects to.
Okay. Okay. So typically for like processors and like separators, you would go to the group and not the object itself. Then.
Right.
Okay.
Right. Yeah. And the only thing that's a little bit different about that for operators is that we don't define a group for the operators. We direct the parameter to the dispatcher.
Got it.
So if you're making copies of an object, you never direct it to the object. You always direct it to some kind of a grouping mechanism, either an object group in the toolbox or a dispatcher in the model.
Cool. Thank you.
Yep. Okay, now these two parameters are actually fairly complicated because they need to look at an object like the dispatcher or the group and do something with the members of that association, something about like the objects that are related. Some parameters are actually really simple and straightforward though. Like for example, if I make a third parameter and say this is going to be my failure rate, I can say that this value is a continuous value. And let's say that our lower bound is a 5% failure rate and our upper bound is a 20% failure rate. And what I want to have happen is that I want the value of this variable, the value of this parameter, to be interpreted by the processor. And I'll just put in my unit. This is a %. And so instead of using something like the reference field to say, oh, I want this to change something about the processor, instead I'll go to the processor and say that I want the processor to use the value of the parameter as part of its regular logic. So remember that we're managing the failure rate by going to the send to port area of the processor. And right now we say that there's an 80% chance of success and a 20% chance of failure. So instead of putting in the values 80 and 20, I can say instead that I want to look at my model dot parameters and then put another dot and reference the name of my parameter, which in this case is failure rate. So now the percentage of flow items that will get sent to port number 2 is whatever the current value of your parameter here is, which right now is a 5. Now, because I'm saying that the failure rate is whatever value is in the parameter, that means I need the leftover amount to also account for that parameter. So I'm going to say 100 minus model dot parameters dot failure rate. So now instead of using like those hard-coded values that I put in, I can tell the object to reference the parameter value directly. And so if ever I change the failure rate in the parameters table, either manually or through an experiment, then that value will automatically be updated on the processor.
Should the parameters be capitalized, or is that the normal?
You like why I said failure rate here with capital F?
Oh, no, like the parameters in purple instead, because isn't the,
That should be lowercase.
okay, that should be lowercase, okay.
Yeah, if the text doesn't turn purple, then it's not right.
Oh, okay, so that's not pointing to that table itself, that's just like that. Okay, got it, I think I get it. Cool.
When you change the port for the operator, when you're sitting in that dispatcher, which did you click to change the ports of who goes to what? Because when I click ports on my operator, there's just nothing.
Oh, so if you go to the ports properties, remember that on the drop-down menu, you choose what kind of port you want to look at.
Got it. Maybe that'll help them. I can't even choose the drop-down.
Can you share your screen with me?
Yeah. So I click any of these ports. There's just nothing.
Okay.
There.
So that's a bug in the UI. So let's go to your view menu and say open default workspace. I don't know why that happens, but it happens sometimes. So now you should be able to see the options under ports.
Nice. That's better.
Yeah.
Thank you.
Can you show the syntax again on connecting the ports to the model? All right, that. I was just wondering if it needed to be in quotes or anything.
Yeah, it looks just like that. Yeah, so this is an example of using a fairly simple parameter, right? Because this parameter is just a number between 5 and 20. It gets interpreted by the processor as a failure rate because I said that I want you to use that parameter value here as part of your logic. So some of the parameters to a model can be really complex, like what we did with the team size, where we said that we want to use this parameter as a way to know how many objects should be connected to the dispatcher, or how we use this parameter to know how many objects should be in this group of objects. But in this case, just using the number, if it's just a simple numeric value, it's really easy to plug that into an input field for an object property and use it that way, if that's all it needs to be. I didn't need to like use the reference field and associate it with the processor or anything like that. I could just say, yeah, just go ahead and use that value directly.
Can
Hey,
you
Regan.
where,
Oh.
well, go ahead, go ahead.
I was going to ask, like for instance, you just set those parameters for the processor one, but there's actually two processors there. Would we need to go back and set that same for both of those processors?
Actually, I just realized that I had made that change on the copy, not the original. If you do
Right.
this on the original object, then it gets copied by the clone as well.
Ah, okay. I did
So-
the same thing and I looked and they were different. So,
Yeah.
okay.
Yeah. So as long as you do this on the original object that the other parameter is copying, then it all works out fine because it just gets cloned as part of the same parameters or property set of the processor, when the other one is made. So, oh wait, I forget to actually paste it. There we go. Oh, port number. Ugh. Mistakes.
So I had a question.
Yes.
In what scenario would we use, let's say, the parameters to have, put in a value and, very similar to what you did now in terms of ports and percentages, and where would we use the global tables? Why would we choose, which situation we choose either over the other?
Yeah, that's a good question. So the nice thing about the parameters is that the experimenter knows how to automatically change those values. And back in the old days, before we had, old days being about, 3 months ago, we would have you actually make a global table and create your own version of a parameter table, if that was something that you needed to do. And so there's still a little bit of overlap between them because this parameter idea is kind of a newer idea to like formalize in the software. But the real advantage to the parameter table is the ability to have the experimenter automatically change those values. So if you have inputs that you want to be able to adjust in the model, but they're not necessarily parameters that you want to be able to experiment with, then you could use a global table. But yeah, and some of the we're using fairly simple parameters here that are just using simple numeric values, like team size of 1 and number of machines of 1 and stuff like that. But you can make the parameters do some really interesting things like substituting different pieces of code in the model. So I would say that it's probably better to get used to using the parameters for the really important inputs of interest that you want to be able to adjust as part of an experiment. But you could use global tables for anything else that wasn't going to be adjusted by the experiment. Does that make sense?
Yeah.
But another thing that you can do too is you can have your parameter actually change a value in one of your global tables. So you could still manage it that way too.
Mm.
So there's a lot of flexibility. And we're still kind of figuring some of that out ourselves, because global tables have been part of the software, for like 20 years. And, parameters have been around for, 5 months now. And we're still trying to figure out okay, well, there's a little bit of gray area between them, but really the strength of the parameter is how it gets used in conjunction with experiments. That's really kind of the big differentiating factor, I'd say.
Okay.
Okay, so as you can see, I've just gone ahead and set my parameters to be what I consider kind of like a baseline scenario for the model where we have one team member, we have one machine, and a 20% failure rate. Okay, so back to our steps here. So now that we've set up our parameter tables, we've set up our performance measure tables, we're now in a position to conduct our experiment. And so, like I mentioned, this is kind of like a more formalized version of experimenting. We've been doing some informal experimenting where we change some object properties and run the model and see what happens. But again, the nice thing about the experimenter feature of the software found under the statistics menu is how it automates this process for us using our parameters, and it allows us to automate this act of conducting an experiment. So if we go to that option under statistics and we say open the experimenter, So one of the things that you'll notice here on the first tab is that the experimenter wants to know which of your model parameters to bring into the experiment, right? So if you click the parent node up there, it just is going to bring everything in. And so it says we've got a parameter for team size, number of machines, and failure rate. And notice that it defaults the values of those parameters to their lower bound. So one team size, because that's the lower bound, one number of machines, 5% failure rate, all because those are the lower bounds that are set in those variables. So it doesn't import the value from the parameter table. It just imports the parameters themselves and wants you to set the values for this scenario. So what I like to do whenever I conduct an experiment for the first time is to create a baseline scenario that I can compare all my other scenarios against, right? So my baseline scenarios, I have one team member, I have one machine, and I have a 20% failure rate. And kind of what I want to do here is I want to experiment with what changes of these values is going to have an effect on my outputs. So that's kind of where we're headed. But for right now, we're just going to leave the baseline scenario as our only scenario. And then I want to go over to the experiment run tab. And this is where we're going to configure the rest of the experiment. So one of the first values you need to put in here is the number of replications per scenario. Like we mentioned before, a single replication of our model really doesn't tell us very much. As with anything in statistics, a small sample size is kind of inconclusive. So we want to run a number of replications that gives us a reasonably good set of data so that the data that our experiment collects is useful. So it actually tells us something. So a lot of people then generally ask at this point, well, how do I know how many replications per scenario to run? If more data points are better than fewer data points, then why not just come here and say, yeah, let's run 1,000 replications per scenario, right? Well, you could do that because big sample sizes are good and everything. However, this is probably too many replications because your model does have to run. It has to execute all of the events that it wants to execute, and it needs to run for the duration of time that it needs to run for. So 1,000 replications for each scenario is probably going to be too many, especially if your model has to run for a really long duration of time before it begins the next replication. So generally speaking, the rule of thumb that like DOE people and Lean Six Sigma folks say is that a reasonable number of replications to run is probably about 30. But like we said, bigger sample size, good. Too big a sample size, bad in terms of actually getting the experiment finished. So usually you can use around 30 as a reasonable value. I probably wouldn't go any higher than 50, honestly. It's probably too many. Because usually about 30 gives you a good set of data where all possible outcomes are reasonably well represented without taking so long to run that it takes forever for the experiment to actually finish. So that's what I tell people usually, a reasonable number of replications, about 30. Now, over in the next set of values, we need to establish the time-based parameters for our experiment, how long a single replication is going to last, and whether or not we want to utilize a warm-up time. So you can define the duration of a replication using either the calendar date and time, or you can use the runtime where you can just indicate a number of time units that you want the model to run for. So you might do something like say, well, let's switch the unit to hours, and let's run the model for 9 hours. Let's run the model from 9 to 5. So notice how updating the runtime automatically updated the end time, because it's just showing you another way of viewing the end time. If you did it the other way around where you updated the end time, that would also automatically update the runtime. So it just gives you two different ways of switching that value. Okay, now then we also have the warm-up time where we can decide whether or not we want to retain statistics from time 0 of the model up to some point where we consider the model warmed up or primed. And just so that we have some experience doing it, I'm going to say that our warm-up time is going to last for 1 hour. Okay, now the interesting thing about this, this means that the model is going to run from time 0, 8 a.m. until 5 p.m. But the first hour of the model runtime is going to be excluded from the statistics. So that means that even though we've said that the model runtime, the replication duration is 9 hours, we're removing 1 hour worth of data from the results. So that means that even though we're running the model from 8 to 5, we're only retaining the statistics from 9 to 5. Does that make sense?
So if any pallets go through in that 1 hour, they're not going to count into the statistics.
Correct.
Got it.
So that's something to think about when you're using warm-up time, is think about how that might potentially influence your actual statistically gathered data set, right? Because we're excluding an hour's worth of data from the model, right? And so that might influence how long you want to run your model for, or how long you want your warm-up time to be. So just consider that interaction where a runtime of 9 hours with a warm-up time of 1 hour means that only 8 hours of actual data will count towards our statistics. Okay, now one other change that I would do to the experiment configuration at the very beginning is to always check this box that says save statistics data for each replication. Now that's an optional option that you can set. Optional option, that makes sense. But it is a useful one for using dashboards to help analyze our model. If you don't have this checked, then the only output measurements that we can really use for analyzing the results of our model are the performance measures. But if you check this box, it lets us do some cool things with our dashboard charts after the experiment is finished. So I would say just always have that checked. It's more useful if you do, and it's kind of a bummer if you forget and you have to check the box and then rerun your experiment so that you can do some neat data manipulation with the dashboards. So I would just say always have that checked. And the other ones are more about like debugging a model, where it just allows you to work with different states of your model after the experiment is finished. And they're not really that important unless something in your experiment is broken, or the experimenter reveals something in your model that is broken, which happens sometimes. But for right now, for just doing what we're doing, we're just going to say, check that first box and don't worry about the other two for now. Okay, so now we're in a position where we can actually run our experiment. So we'll find that big run experiment button and we're going to say run. And so we're going to see this red bar pop up that represents the progress of our experiment. And as the little sub bars turn from green to red, we were finishing replications of our model. So this is one area where having a lot of processing power on your computer is really going to be useful. If you have a lot of logical cores on your machine, then you'll be able to run a replication for each core. So if you have like a really beefy 12-core machine, then you're going to be able to churn through an experiment really, really quickly. But notice that while the experiment was running, nothing happened in my model out here because these replications of the model are being run as like background processes, and then they just report their data back to FlexSim. And now that they've finished all of their replications, we can view the results by clicking on the little view results button here. And it gives us a little report. So this is the result of our total throughput using our baseline scenario parameters. So again, I'll let us see those parameters. So with one team member, one machine, and a 20% failure rate, the total number of pallets that we can expect with a 95% confidence interval is on average 45.7 pallets for that 8-hour period. And each of these red dots represents a replication value. So we can see that we had 42 pallets for replication 20, 45 pallets for replication 23, 51 pallets for replication 27, which represents our maximum. Our minimum is down here at 41, and our median is 45. And with a 95% confidence interval, our mean is from 44.6 to 46.7, and our sample mean 45.7. Now on this drop-down menu up here, I can switch to one of my other performance measures. So if I want to look at my pallets per hour, this means that my pallets per hour is 5.71 as a mean, my maximum is 6.38, and my minimum is 5.13. And so the replications plot is one way to view the results of our performance measures. You can also look at a frequency histogram and see the distribution of values for our pallets per hour. So we can see that most of our pallets per hour were in this range. We had 6 replications that fell between 5.5 and 5.63. If we switch this over to our throughput, again, same kind of thing, where we can see the distribution of values across the x-axis. You can also look at our correlation plot. So a correlation plot allows you to correlate 2 variables together. So if we correlate total throughput with pallets per hour, no surprise, that's a perfect positive correlation, because as throughput goes up, pallets per hour goes up, right? But if you had different variables that you wanted to try to correlate together, this could be a useful view where you could say, well, I want to correlate maybe operator utilization with the content of a queue or something like that, and see how busy my operators are correlates with how empty a queue is, or something along those lines. But you just need at least 2 performance measures to use the correlating plot, because you have to be able to correlate one performance measure against a different performance measure. And then on the data summary, we just get a little summarization about our min value, our max value, our sample standard deviation, and our mean using our confidence interval of whatever you choose here, 90% confidence, 95, 99% confidence, whatever confidence interval you want to choose. And then there's also the raw data, which gives you a table view of the performance measures. So here are the individual data points for throughput, total throughput, and then here are the average, or the pallet per hour data points for each replication, which is really just showing you the same stuff that's on the replications plot with each of these red dots. Just showing it to you in table view instead.
What was the total throughput tied to again?
That's
like when you did it in the dashboard, and you
that's the input of the sync.
Input of the sync. Okay.
So that's the input statistic associated with the sync object. So it's looking at the throughput, the input average to the sync object. I connected that to the sync's throughput chart that we made earlier.
Yeah. Okay. I didn't do that when you did it.
How would we make this, let's say, a little more granular? Let's say we're running an experiment or one replication is for a year, but we want like a weekly average or a monthly average for.
Yeah, I think you could do that with in the dashboard chart. There is an output by hour, and this is a newer chart. I haven't really used this one very much yet, but the output by hour allows you to choose an interval, either weekly or daily. It looks like it doesn't go as high as like monthly. But what this would do is this would break down your throughput by different hours of the day instead of an average, instead of the rate, right? Like what we have right now is the rate, like how many pallets per hour. But if you do the output by hour and did like a week, that would give you like, you know, this is how much throughput you had during week 1, week 2, week 3, something like that.
Okay. No, but
I think that would give you closer to what you're looking for.
Would we get that in the raw data section? I mean, in the raw data section, you showed a bunch of columns which represent a replication, correct?
Yeah, in the raw data section, yeah, that would be just showing you the individual replication values for the stat that you're measuring.
Got it. And we won't be able to, if let's say for each replication, we want it to be shown as a 52 rows for 52 weeks, average of each week, that we won't be able to get the data, or will we be able?
Yeah, that's interesting. I'm not sure what kind of options it would give you to do that. Let me just add a performance measure really quick. If you measure this, if you do the all data average, Yeah, probably what you'd have to use is, instead of doing that as a performance measure in the performance measure table, you probably have to take advantage of basically what this checkbox gives you, the save stats data for each replication, where we can use the data gathered by the chart as a way to display an experimenter version of the chart using a chart that's called the scenario chart. We're going to talk about that in a minute.
Okay.
Because that would just show you the chart, but using the experiment data instead of like a single replication data or something like that. That'd probably be the better way to use that one, because it'd be a more difficult chart to use because it doesn't have a single value that is the performance measure, right? You're more looking for like a charted thing, and the scenario chart is better at displaying that.
Got it. Okay.
Yeah, I'll do an example of that though.
That will be helpful.
Okay. So that's the nice thing about the experimenter, where it automatically runs the model a bunch of times and gives us these nice aggregated reports. But now if we want to actually compare what happens if we change certain values here, then we can go back to our scenarios table and say, let's add a scenario and see what happens if we change any of our variables. So let's maybe have a scenario that's called add a team member. And I like giving the scenarios names. Just helps with the comprehension on the reports. And so we'll say, let's add a team member. So now team member size is 2, but we'll keep the number of machines the same and the number or the failure rate the same. Let's maybe have another scenario that says add a machine. We'll only add that, and maybe we'll have another scenario that says lower failure rate. Oops. So again, we'll keep number of machines at 1, number of team members at 1, and our 5% failure rate. Let's just see what happens if we change any of these 3 performance, or these 3 parameters independently. So if we say reset the experiment, rerun it, now we're going to run 4 scenarios. And we want to see what happens. Like, if we add a team member, does that give us more throughput? If we add a machine, does that give us more throughput? If we lower the failure rate, does that give us more throughput? And so you can kind of see, the more scenarios you have, the more replications per scenario, the longer your experiment takes, right? But again, the better machine you have, then the easier it is to run these experiments. So if we view the results now, and we'll plot the mean at 95% confidence. So again, our baseline, we'll look at the pallets per hour, baseline 5.71. If we add a team member, we get 6.53. So we added almost a full pallet per hour. If we add a machine, we get almost a full pallet per hour. If we reduce the failure rate, we get about a half pallet per hour, a little bit more like 3/4 of a pallet per hour. So it looks like adding any one of those things by themselves gives us a little bit of a bump in throughput. And if we look at the data summary, we can also see that there's standard deviations. Like our lowest standard deviation is with the baseline. We get a little bit more variability if we add a team member, a little bit more variability if we add a machine, and a little bit less variability if we lower the failure rate. So you're kind of balancing here, thinking, well, which of these do I think has the greater impact? Well, their mins and their maxes are fairly comparable. Their standard deviations are also fairly comparable, and their averages are fairly comparable. So that's interesting. So what if we went back to our experiment and said, okay, well, what if we wanted to maximize throughput? What if we said, okay, let's get rid of those. Let's add a scenario that says max throughput, and we say that we've got 3 and 3 and 5%, right? And so if we run that experiment now,
should my data look exactly like yours?
It won't look exactly the same because the layout of the model has an impact, because there's travel time to be accounted for.
Okay.
It'll be close, but not exact.
Yeah, I agree, because my throughput numbers looked considerably different than yours. The pallets per hour always ended up about the same, but my throughput range was a lot smaller.
Yeah, that can be impacted by like if you have a processing time still on your separator or your combiner, all of that could have a potential impact, as well as travel distance for the operator. That could also have an impact. Okay, so what's interesting here is now if I tried to maximize throughput, I gave myself 3 operators, 3 machines, and a low failure rate. I can't quite seem to get over that hump, right? Where my average is 5.7. I still got myself about 1 more pallet per hour. So there seems to be some diminishing returns with these parameters that I've given myself. Right? Because if I were to add more operators or more machines, it seems like this is as far as I can get on maximizing my throughput based on what's happening in this part of my model. So that's interesting. And that's something that comes up, right? You might make assumptions about the way your model works. And in the course of doing an experiment, you might find that your assumptions were incomplete or they weren't right? Because if we were assuming, well, if we just had more people working on processing things over to the combiner area, then we should be able to increase our throughput pretty well. Well, it turns out that that's true to a point, but you could get the same results as we got here with the 3 machines, the 3 workers, and the low failure rate as you could by changing any one of those parameters by just like 1 value, right? The change in throughput of going from 1 machine to 2 machines and everything else remaining the same is about the same as trying to give myself a lot of available resources. So this might lead you to then ask yourself, well, how can I figure out where the true bottleneck is in this model? What are some other options that I have to figure out like where I'm spending a lot of time? Well, this is where something like the scenario chart might become useful. And the scenario chart is a way to create a chart based on your experiment data for other charts that you've already created into your dashboard window. So I'm going to make a new dashboard window. And in the library, I'm going to bring out my scenario chart. And in my scenario chart, I'm going to say that I want this chart to copy the data for my content versus time chart and to show me the data for the baseline scenario and the maximum throughput. And so what it does is it draws a line for each replication of the scenario. So the orange lines are my baseline scenario, the yellow or the green lines are my maximum throughput scenario. But if I come to the interpolation area and say that I want to do this as a stair step, then it kind of puts it into like a horsetail graph a little bit where I can see that in my baseline scenario, yeah, the content of my queue was a problem. I had a lot of things waiting to be processed, but in my maximum throughput scenario, I had almost nothing waiting to be processed. So clearly this is not the bottleneck beyond a certain point. And so using different tools like this, you might try to figure out, okay, where is my problem? And so another thing that you might do to try and find the problem, I'm going to make another dashboard. Actually, no, I don't want that third dashboard. I want to go back to my first dashboard. So what if we were to add all of these queues? It might be interesting to see what is the content of these queues, because what is the time spent in these queues seems to be a potential problem. So I'm going to add a work in progress or a content chart. And I'm going to add each of these queues. And I'm also going to add a stay time chart and also add each of these queues. And then I'm just going to go back to my experiment. And I have to reset the experiment and rerun it because I added new charts that I want to get their data for. And then back on this chart, instead of looking at my content versus time for my first queue, I can say, let's look at the content chart. And so let's make this a little bit bigger. A little bit hard to read. So the content average for Q3, which is the part number 1 queue, was 56, 17 for Q2, 141 for Q3. Or no, I'm sorry, I read that wrong. Q5, baseline scenario 3. And so we're kind of seeing that those contents, but you look at Q6, where its content is 0. So that's interesting, right? And if we were to say, look at the stay time, then in the max throughput scenario, our maximum stay time in Q6 was the lowest out of all of them. So it appears that potentially my problem is that I'm waiting around a lot for Q6 to give me boxes to the combiner. And it looks like I have way too many things in Q5. And a lot of things in Q2 and a lot of things in Q1, but Q5 looks really bad. So this might lead me to believe then that my mix of products is probably my bottleneck, that I'm creating too many things that are going to Q5, too many things that are type 3 or part number 3, not enough things that are part number 4, because my queue for part number 4 is starved in the max throughput scenario. I reduced the stay time a little bit, right? We went from a stay time of 78 to 55 by going from baseline scenario to my max throughput scenario. But the problem really seems to be that I don't have enough things going through Q6. And that's why my throughput has hit a wall, where there's just only so much these guys back here can do to reduce or to increase the throughput of things to the combiner. That looks better. And so that's where the dashboard charts can actually supplement your experiment. If you have that checkbox checked, it allows you to do some neat things with the scenario chart, where you can take the data that you've already gathered in some of these charts and display them using the experiment data rather than just a single replication of your model. And the nice thing about the scenario chart, you can toggle this around any way that you want to change the chart that you're showing on the scenario chart, or you could create multiple scenario charts. That's fine too. But if you just want to like quickly check on some of the data from your dashboard charts that you have, this is a fine way to just kind of go through and see what they are, as another way to help analyze your model. Okay, so I threw a lot of stuff at you there. Any questions at all?
I have a question. I mean, it's more just for argument's sake. Q6 is probably part 4. Didn't we give it a uniform distribution in the beginning? So are we good to see that the parts are producing at a very different rate?
Yeah, so in this model, we're actually using this empirical distribution.
Yes, correct.
Right? And so you can see that, even though part number 4 makes up 27% of our product, more or less, that's not enough to keep up with demand. And that makes sense too, because if you remember on the combiner, we need 5 things from that queue to complete a pallet. And it's only sort of like medium production rate. But we're clearly making too many of these because that only requires 3 things. So that might be a fun parameter to go in and make after we've kind of done this, to say, oh, we've learned some things. Might be a fun parameter to be able to change the weighting to try and maximize throughput by adjusting the weight parameter on the empirical distribution. And unfortunately, right now, that's not like super easy to do. Otherwise, I would do it just to show it to you. But that is something that is coming to be a little bit easier. But right now, it's a little bit of a pain.
Okay. Yeah, I understand.
But that would be something interesting to go, oh, wow, look at these results. I didn't expect that. Let's adjust the weight parameters of our empirical distribution and see what the right mix of products is to maximize throughput. That'd be a cool experiment.
You talked about optimizers, but that's not going to be covered in this lesson. Like for my work, like I know like one of the questions that they're going to want me to answer is like, what is the minimum equipment needed to get the specific throughput, maintaining this cycle time, right?
Mm-hmm.
Like, is that something that the optimizer would be able to answer, or would
Yes.
I have to do? Okay. And
Yeah.
how would I get that?
So you set up your model for the optimizer the same way that you set up for the experiment. You define parameters, you define performance measures, but then what the optimizer does is it takes your upper and lower bounds for your variables, and then you give it an optimization algorithm that says, I want to minimize for this performance measure, I want to maximize for this performance measure, or something like that. And then it will try to find the right parameter values that you've supplied it in order to either min or max or whatever the performance measure that you give it. So setting the model up for the optimizer is a lot like setting up the experimenter. The difference is with the experimenter, you're trying out your own values to try and find the quote unquote best scenario, whereas the optimizer runs an algorithm to try and find it for you.
Got it.
You just have to tell the optimizer what best means, right?
Mm-hmm. Sure. Thank you.
Yep. All right, guys. Well, why don't we go ahead and take our midday break? We'll do some lunch. And when we come back, we are going to explore some additional tools that we have to help us implement our modeling logic. After spending a lot of time with the object stuff, there are more tools to discuss. And so we'll shift gears to discussing that stuff when we come back from the break.
Sounds like a plan.
All right, we'll see you in an hour. Okay, so welcome back. And like I said before the break, in this next section, we are going to focus our attention on another set of tools that we have available to us to help us build models. Relatively speaking, to the rest of FlexSim, it's a relatively newer feature. It's been around since 2015. We call it process flow. And essentially what it allows us to do is it gives us a more visual way of creating and implementing customized logical behavior in our model. So the way process flow works is that rather than giving you control of your model at like an object level, right? The objects themselves come with a lot of predetermined behavior. What process flow does is it gives you a way to determine a lower level of detail, a greater degree of control over your model than what you get with the objects. Now that kind of comes with the double-edged sword. Like the good news is you get to do whatever you want. The bad news is you have to describe everything that you want to do. So process flow is extremely strong in the areas of customization and flexibility. You can really define any kind of logic that you want with process flow, but it does put a lot more responsibility into your lap, because unlike the objects, they don't make as many assumptions about what you can do in a model in order to make your life easier. Like consider things like processors and queues and port connections, where they make a lot of assumptions about the way things are going to work together. And a lot of the difficult logic of making objects coordinate with each other is just handled for you naturally behind the scenes. You don't even have to think about it. Now, the nice thing about that is that it just does it for you automatically. But sometimes the downside of that is that we may have made an assumption about the way the objects work together that may not be valid for your model. And so that's why tools like process flow are very useful to be able to come in and say, well, the way that this is defined in the object environment maybe isn't exactly the way that I want to do it. So I want to take control of this aspect of my model myself. So when using process flow, it's not an either or decision. It's not either you're going to build a model with process flow or you're going to build a model with objects. There's going to be times when objects do things that you want to do, that you want to be able to do, and you're going to take advantage of them. And there's going to be times when process flow might make it easier to do something that you want to do, and you'll take advantage of that in the same model. So it's not really so much, well, geez, how do I know what library to choose? It's more about being able to say, okay, what do the objects give me that I like to use and take advantage of? And what does process flow give me that I want to use and take advantage of, right? And so there's going to be, in almost every model that you do, there's going to be like a sliding scale of how much object environment or like how much object library based tools to use versus how much process flow based tools to use. Now, since process flow gives you so much in the way of capability, we end up focusing a lot on process flow in terms of like our new development in the software, because we find that it's a lot easier to define complex behaviors with process flow than it is with the objects. So the objects are always going to be there as a way to make it easier to do things, kind of an out of the box way. But process flow is going to be something that you're going to want to take advantage of in order to increase the customization and flexibility of your models. Now, one thing about process flow is, if you recall this flow chart, I mentioned yesterday that an object is essentially a collection of modeling events. It's a prepackaged collection of events. It already knows how to do certain things. And these events are triggered by the presence of a flow item. And you can kind of think of process flow as a way to define your own flow charts, your own customized sequence of events at the event level of your model, as opposed to like this higher level object level of your model, where you can define any sequence of events that you want that are caused by anything in your model that you want. And basically a way to just say, I want to do a bunch of stuff that FlexSim objects potentially don't know how to do natively. And you can just say, here's my events, here's my process flow that defines like this kind of a flow chart behind the scenes of an object, but you get to define it yourself. So it happens how you want, where you want, when you want, in the order that you want, without having to worry about any assumptions that an object is making on your behalf. Does that make sense so far? Anyone have any questions? So there are three primary concepts in process flow to get familiar with. The first is this idea of an activity. And an activity in process flow is essentially how you define behavior. So most activities, in fact, well, really, I shouldn't say most, all the activities are really designed to be very simple, very focused. They know how to do one or two things, and that's about it. So each individual activity in process flow is very simple, and it becomes a very simple building block of the logical structure that you want to build in your model. And so this is by design, that each individual activity is very simple. The point with the activities is to do less for you automatically, so that you can use more of these simple activities and put them together into a larger structure of logic. And so you have control over the activities about what order they're done in, input settings that they have, you have control over those. But by and large, the activities really only have a couple of options that you have to worry about. So again, that's kind of in contrast to the objects, where the objects represent a larger collection of events and a larger collection of configurable properties, because they do a lot for you automatically. Whereas again, the activities do very little for you automatically and are designed to do like their one thing that they're designed to do. Now, the way that we cause activities to execute their logic is through the creation of what we call tokens. So a token we come across tokens a lot of ways in everyday life. Like anytime that you don't pay for something with cash, you're basically using tokens, where you're using one thing to represent another thing. And like in the case of like credit cards and stuff like that, you're using that as a substitute for actual money that represents. And so this idea of tokens is really caught up in the idea of representation, where tokens are used to represent things that follow the flow of logic defined by your activities. Now, you could think of tokens as being similar in concept to flow items, but they are fairly different, distinct things. They are similar in the sense that they both flow from point to point in the model, causing logic to execute as they move along. But whereas flow items are assumed to represent a physical component in a physical process, actually going from an object that represents a location to another object that represents a location, tokens are used more in the abstract sense, where they represent the flow of logic, and less about moving from place to place, and moving from and more in terms of moving from step to step. And so tokens are used to represent this idea of logical progression. And so as we follow a token through a flow of activities, we follow the sequence of logic that the token is causing to execute. Does that make sense so far? Okay. Well, let's take a look at an example. So if I just come back over to a model, I'm just going to make a new model. I'm going to start totally from scratch. I'm going to choose my model units the same way that I always do. And again, the first thing that I'm presented with is the grid. But if I want to supplement my model with process flow logic and behavior, then I can come up to the process flow button in my toolbar. And this gives me some different ways to apply process flow to my model. Now, there's a few different kinds of what you might call a flow. There's a few different kinds of flows that you might take advantage of here. But really, the only one that we're going to be concerned with in this class is the idea of a general flow. So that's what we're going to create here. A general flow just means that it's a generalized process flow. It's not associated with any specific object or assuming any specific kind of behavior. It's really kind of a blank slate, open field, where you can define any kind of activities that you want, and doesn't make any assumptions about how it's going to be used. And really, for the vast majority of things that you do in a model with process flow, you can do it with a general flow. You only have to use one of these other flows if there's something specifically that these kinds of flows might give you access to. But by and large, everything that you want to do, you can really do with the general flow. So that's the one we're going to focus. Okay, now the first thing that you'll notice right off about the process flow window, or canvas, if you want to think of it that way, is that it is a two-dimensional environment. So the two-dimensional environment of process flow allows us to create the activities and define the flow of events that we want process flow to execute for us. So if you click on the process flow window, notice that your library over on the left-hand side has changed. So it no longer displays the objects that we bring into the grid, but now it gives me a set of activities that I can bring into process flow. And if you click back on the 3D grid, you're back to your 3D object library. And if you click on process flow, you're back to your process flow library. Now, one of the things about the process flow library that you might notice right off the top is that there's a lot going on in here. There are a lot of individual activities. And the complexity of learning process flow and knowing how to use process flow is usually in understanding what each of these different activities do. And that can feel a little bit intimidating because there are a lot of potential activities to choose from. But when you remember that they're all very simple and they're all designed to do basically one thing, hopefully that doesn't make it feel as like, wow, there's a lot going on in there. And really, once you start to learn how to use a few of these activities, looking at the options of the other activities is pretty easy to understand once you get exposed to the way these things are designed. Now, in a process flow model, we need to start with a way to create tokens. And so the first activity I'm going to create as an example is going to be found under the token creation section of the library. And you'll notice that we have 4 activities here that are called sources. So right away, this is a pretty big contrast to the way we handle creating things in process flow versus in the object environment, where in the object library, there is only one source. There is the source, and that creates flow items, right? In process flow, we have a lot of different sources. They all create tokens, but they create tokens using different patterns. And so rather than try to make one source activity that knows how to do all of this different stuff, which would make it very complex and harder to use, we instead broke all of these different ways of creating tokens into individual activities, again, keeping with the design philosophy of trying to keep things simple and focused. So each of these source activities defines a different pattern for how you might want to create or how you might want to create tokens. The inter-arrival source is the most similar thing to the source object that we've seen so far, where you can drag out this activity. And if you click on it, whoops, you'll notice on the right-hand panel, you have the properties for this activity, just like you have with the objects, but also notice that the amount of properties is much decreased compared to the objects. A lot less happening here. There's a couple of checkboxes. There's one really important edit field and then an optional edit field, and nothing really else going on here. The only thing that this activity knows how to do is to create a token according to this inter-arrival time. And you'll notice that when you click and drag on the activity, you can move it around just like you would with something in the 3D environment. But again, noting the 2-dimensional abstract nature of the process flow environment. Now, if I were to also create a source object, okay, and I'm going to open up our event list. Remember the event list from yesterday, hopefully, where we see the events that are scheduled to happen in our model. Now, if I hit reset, right, we have in an event for the source object that says that we are going to create a flow item at time 36.19. And we have another event that says that we are going to have a process flow source event that is going to happen at time 5.82. And that's going to create a token for us. So the reason why I'm showing you this is because I want you to understand that the events in the model can be created by object-based tools, or they can be created by process flow-based tools. They're all events in the same model. So the source object is going to create its flow item according to its properties, and the source activity is going to create its token based on its properties. And they're completely separate from each other. They're just generating their own events into the event list and causing the model to react to the events that we execute, whether they come from the object side or whether they come from the process flow side. Okay, now if I allow the model to run now, I want you to notice that the source activity is generating tokens. And those tokens don't have anywhere to go, so they are still just being created. And we can see the event in the event list that says that the source activity is going to continue to create tokens. The source object created one flow item and stopped because it assumes that if it doesn't have anywhere to send that flow item, then it should stop creating flow items. The source activity does not make that same assumption. It assumes that if you wanted to create a token every 3 seconds according to the exponential distribution, then that's what it's going to do. And it has an unlimited capacity to hold those tokens because it's just going to create more tokens. Just because it doesn't have anywhere to send it doesn't mean it's going to stop making those tokens. It just keeps on going. So this is a pretty big contrast between the two sets of tools again. Even though their jobs are similar, they're both supposed to create something, they go about it in different ways. The source creates a flow item, and if it doesn't have somewhere to send that flow item, then it stops creating flow items. The source activity creates tokens, and if it doesn't have anywhere to send those tokens, it just keeps making tokens, assuming that we're going to do something sometime that will allow these tokens to flow to some other activity and do something. But it is going to follow its arrival pattern using that exponential distribution no matter what. Oh, and by the way, this is another way of viewing the properties of the activity. If you click on the icon then it pops down this window. It's the same set of properties that you see in the property panel on the right-hand side. Same thing, just different ways of interacting with it. Okay, so let's give our tokens here a little bit more to do. So I'm going to drag out just a couple more activities, just keeping things simple still, just so we can show how these activities can interact with each other. So notice that when you drag out these activities, you get these little guidelines, kind of like in a PowerPoint slide to show you how these things line up. So I'm just dragging out a couple of delay activities and a sync activity. So the job of the delay activity is to cause tokens to be delayed according to some delay time. And again, notice the simplicity here, where the only input to this activity is the amount of time that you want the token to be delayed. And just like what we saw with the processor, you can type in just a value here. You could say that there's a 10-second delay, or you could say there's a delay that's based on a distribution. If you go to the drop-down menu, you get options that allow you to choose things like distributions to say how long a delay is going to last, or a number of other ways that you might cause the delay to be executed. And so just having these activities out here, though, isn't enough. If I hit run again, then those tokens are going to just continue to pile up at the source activity, waiting to go someplace else. So how can we send tokens to another activity? Well, in the process flow environment, we've tried to make this a little bit simpler compared to the object environment with the port connections and everything. So what we do instead is we take an activity like the delay, and if you want to, you can just drag this activity up into the source, and they dock together into what we call a stacked block. So this becomes a block of activities, which means that the first activity in the block will happen first, and then the next activity in the block will happen second. So if I were to drag all these together into one single block, this would mean that we are going to execute the source activity first. It's going to create its tokens. Then we're going to do the first delay, and then we're going to do the second delay. And just to kind of help differentiate this, well, I'll call this delay 1. And I'll call this one delay 2. So we hit reset and run. Tokens immediately are released to the first delay. They execute their delay time, and then they're released to the second delay where they execute their delay time. And then when they reach the sink, they're destroyed, because the job of the sync activity is to remove tokens from the model. But notice that this is purely happening sequentially. Activities happen in the order that they are connected. So if we say that we go from the source to delay 1, then we have to finish delay 1, and then we have to go to delay 2. And then once we're done with delay 2, then we can go to the sync. Now, one of the things that we tried to do with process flow, because it's so abstract, sometimes it's difficult to kind of relate to what you're seeing. So in addition to being able to create blocks of activities, we tried to give you some other ways to visualize the flow to hopefully make things like this a little bit easier to understand. So in addition to creating blocks of activities, you could also allow process flow to mimic more of a flowchart-based environment by creating connector objects between the activities.
You need another shortcut? Was that a shortcut to do that?
Oh yeah, sorry. Let me do that a little more slowly. So when you click on a block of activities, you get these circles around the perimeter of the block. And if you just mouse over that point, it puts your cursor into the chain link mode. So I'm not holding down any shortcuts or any keys. I'm not choosing any modes like I did with the 3D environment. Just by getting your cursor on one of those circles, or even the perimeter, like the yellow perimeter around the activity, you get that chain link appearance. It's just a little bit easier with the circles. It gives you a little bit bigger target. And then if you click and drag, this allows you to drag this arrow to another block of activities. You can see that when that arrow gets close to another block, it does like a magnetic snapping on to let you know that you are attached to the next block of activities. And then when you release, it finishes the connect. And so this way you can have your process flow look more like a flowchart, where you can have connectors that show that you do delay 1, and then you go through the connector to delay number 2, and then out to the sync. But again, the activities are still happening sequentially. We execute the first two activities in the first block, and then we go to the first activity of the second block, and then the last activity of the block. Any questions so far? Okay. Now, with the process flow environment, we do want you to try to visualize your flows in ways that make sense. Like, for example, if you were to take a connector, you can click and drag that off. And if you wanted to arrange things so that it looked more like this, you know, like you go from here and then over here, or if you wanted to visualize things going like laterally like this, it really is very flexible. And like, it doesn't matter where the connector is connected to the next block of activities. Like this connector is kind of like in between the delay and the sync. But remember that when you send a token to a block, it always goes to the first activity of the block before it goes to the next activity. So even if I were to take this connector and point it directly at the sync, that doesn't mean the tokens go directly to the sync. They always have to go through the delay before they get to the sync, because you always start at the first activity in the block before you move on to the second activity in the block, and so on and so on. Now, another thing that you might be noticing here is that the delay activities don't seem to care how many tokens are present. In fact, the activities in general don't make any kind of built-in assumption about any capacity that they might have. So again, if you look at the properties for something like the delay activity, all it says is this is how long tokens are going to be here. They're going to be here 10 seconds. There's no maximum content. There's no limiting factor. If you happen to send a lot of tokens to that first delay, then they will all execute their delay times as soon as they arrive. And whatever token finishes their delay time will be released to the next activity. So all of these delay times are happening in parallel to each other, depending upon when the tokens actually arrive. And that's kind of a general rule for all of the activities, where they don't make any assumptions about their capacities. So what do you do then if you do want to enforce any sort of rules about how many things are permitted to flow through a set of activities? Well, this is where the third important core concept of process flow comes into play, that we call shared assets. So a shared asset is essentially a way to create a finite resource that tokens may need to attempt to claim or release as they progress through the flow of activities that you define. So there are three primary shared assets that we're going to care about in this course. There's actually a fourth one, the variable. We're not going to worry about it here. But shared assets like the resource, the zone, and the list are ways of enforcing demands for limited assets, limited resources that have to be claimed and released as tokens move through their flow. So for example, things like the resource might be used to represent the limited availability associated with tools or machines or people, where you're saying that there is some abstract idea of a resource that has to be acquired and then later released in order for other claimers to make a claim on that resource and have it fulfilled. The other shared assets, the zone and the list, they do something similar, but in slightly different ways. And we'll talk about those in depth later on this week. But for right now, we're just going to focus on using the resource. So like, let's say, for example, that in addition to delay 1 and delay 2, if I were to drag out a delay activity and drop it right on this connector, right, it's going to split the connector. And let me stick it in there. And I'm going to say this delay is called the restricted delay, or just delay restricted. Now, if I leave it the way it is right now, excuse me, then that means that, like the other delays, I could have an unlimited number of tokens present at this restricted delay. But if I use a shared asset, like for example, I'm going to bring out a resource, then I can make it so that in order to gain access to this delay, you first have to acquire the availability of this resource. So if you take a look at the resource properties, it has a little bit more going on than some of the other activities, but the two most important options are going to be the resource reference, which right now is set to numeric, and the count, which is currently set to 1. So the reference of the resource being numeric just means that this resource represents an abstract notion of availability, and the count represents the amount of availability at the resource. So there is one resource essentially available to be acquired from this resource. And so if the count is 1, that means that there is only one slot essentially of availability that you can use. You can think of it like a parking space. There's only one parking space available. And so if a token tries to acquire this parking space, then it will be in use as long as the token is using it. So how does the token actually gain access to this resource? Well, one thing that you might notice is that if you were to take this resource shared asset and actually try and drag it into these other activities, it doesn't do the docking on action that we saw before with the other activities. And if we were to take a connector and try and get the connector to lead over here, it doesn't, because tokens don't go to resources or shared assets, they access them. And they access those shared assets through special activities that give access to the shared asset. So in the case of the resource, a resource must be acquired, and then it must be released. Now, notice when I brought out that acquire activity, a blue line was drawn between the acquire and the resource. This blue line represents a relationship that says that if a token executes this acquire activity, it will try to gain access to this resource. So if you were to drag out like another acquire activity, notice that it doesn't have that blue link, because we assume that the first acquire activity that you drag out is going to automatically connect to the first resource that you dragged out. I actually really don't like that it does that, but for whatever reason, they decided to assume that this acquire is going to be associated with this resource. To me, that seems like a bad assumption, but whatever. But this acquire didn't automatically link itself up. And instead of having a blue line, it has an exclamation point. And certain activities in process flow will have this exclamation point to signify that they need to be configured in some way. And in this case, with the acquire, it means that it doesn't know what resource it is associated with. And so if you mouse over the exclamation point, it turns into the eyedropper. And so if you left click once, it turns your cursor into the eyedropper. And then you click again on the resource and it connects you to that resource. And by the way, this is okay. Having two activities linked to the same resource, like having two acquires pointing at the same resource, is completely fine. Because the whole point of a shared asset is that it is meant to be shared across multiple flows, potentially, of tokens. And so that would mean that if I had a flow of activities over here that tried to acquire that resource, and tokens flowing over here that are trying to acquire that resource, that would mean those two different sets of tokens would be competing for the availability of this resource. And that's okay. In fact, we're going to do an exercise where that is the desired outcome, to have resources be in competition with each other, which means that they need to provide multiple access points, like multiple acquires, and also multiple releasing points to give control of that resource back to any waiting claimers on that resource. I'll just get rid of that for now. Okay, so let's see what this looks like. If we hit reset and run now, when our first tokens come through, so let me just stop it there for a second. So now we can see that we have one token that is active at the restricted delay. And now we have a queue forming at the acquire activity, as these tokens want to acquire the resource but aren't able to because it is currently in use. So we represent that with a couple of numbers on the resource, where we have the green dot number that represents the number of tokens actively using the resource, and the red dot number that represents the number of unfulfilled requests on the resource. So right now we have 1 token using the resource and 5 tokens requesting the resource. And so if we continue to run, when the token that was using the resource executes the releasing activity, that allows the next unfulfilled request to make a claim on that resource. And so by default, that queue is being handled first come, first served. So whatever token has been waiting the longest at the acquire activity gets its claim fulfilled next.
Can you go over again how you set the resource and how it kind of gates that flow? Is the delay restricted? Is that what's causing it to back up, or is it something that you set on the resource that's causing it?
It's the resource itself. So if I take the acquire and the release out of the loop, right, then that means that unlimited tokens can go to the restricted delay because there's no inherent sense of capacity on the delay activity itself. All it says is that tokens are going to be delayed here according to this amount of time, right? But if I put the acquire in and also the release, then that means that they have to check the availability of the resource to see if they're allowed to progress. So the first token that comes through, when it finishes that first delay, just waiting for it. So right there, it makes a claim on the resource. And because the resource is available, when it does the acquire, it's allowed to move on to the restricted delay. The acquire is essentially acting as the gatekeeper because you have to come to the acquire and say, hey, is the resource available? And it says, well, I have 1 count of availability, and now you have it, right? So now the resource has 0 availability because this 1 token claimed all of the availability associated with that resource.
All right. Yeah, I got it. Cool. Thanks.
And then as more tokens come, they make their claims, but they can't be fulfilled yet because the resource is busy. And then once that is released, then the next token is allowed to come to the delay. Now, the release is really important because if you didn't have the release, you would never know when you gave up control of your resource. So like if I were to drag that release out of there, oh, and by the way, that was a keyboard shortcut. If you hold down the control key and click and drag on an activity, you can remove it from a block. The other way that you could do that is use the scissor icon and remove it. But I like the control drag better. I think it's cleaner. But if I remove that release, right, you're able to acquire. But now there isn't an event that says when you reach this point, give up control of the resource so that others can use it. So we leave that restricted delay. We go to delay 2, and this token still owns the resource. And even when it goes to the sink, it's going to own that resource. And when it reaches the sink, because it's still owning that resource, we don't let you destroy the token if it has a shared asset acquired. So we got to have this release point that says when you reach this point of the flow, you no longer control the resource and you give it up so it can be used by other tokens. So it doesn't matter where you put the release point. I can put it here. I could put it here. It doesn't matter, right? It's up to you to decide where the appropriate point is to release these kinds of resources. Because again, as the modeler, you have control over the flow of events, and it's up to you to decide when the right time is to establish acquisition rules for resources and also releasing rules for resources. And this is an example of one of the things that the objects do for you automatically that you've never had to really think about, but process flow is making you figure out how to handle this idea. Like in this case, this resource might represent the availability of a processor object, and the availability of a processor object is normally handled through port connections. But in process flow, since there isn't an object that needs to be acquired, it's a resource, we have to establish when the acquisition happens and when the release happens. But that's all logic that is handled by port connections quietly behind the scenes. But if you don't like the way the port connections handle it quietly behind the scenes, then it's nice to be able to use these resource shared assets to mimic that same behavior, but handle it in more the way you want to. Okay, any questions so far? Okay. So let's give you guys an exercise to do where we kind of implement these basic ideas of process flow. So similar to what we did with the object-based model yesterday and today, we are going to build a process flow model progressively through a number of phases. So this is going to be phase 1. And everything that we do in phases 1, 2, 3, 4, 5, and so on are all going to be done in the same model. So just kind of progressively save your model as we make changes, as we add things to it, as we build from a simple model to a more complex model. So in this model, we want to do something fairly simple where we're going to create a process flow that produces a token that we're going to say represents a part in a manufacturing process. And we're going to say that the creation rate is according to the exponential distribution with a location value of 0 and a scale value of 30. That part will then need to execute a series of delay activities that represent different steps in the process. So we're going to say that there's an inspection step, followed by painting, and then followed by curing, which have to be done in that order. Now, in this model, we don't really care about the delays associated with, like the delay time associated with these different steps. So just use the default value for the delay time. Just keep it simple. Now, one thing that we do want to say, though, is that there is a single resource available that conducts inspection, a separate resource to conduct painting. But we're going to say that there are 3 curing slots that can be occupied at a time. So we're going to use resources to create limits on how many tokens can do inspection, how many tokens can do painting, and how many tokens can do curing. And once the curing process is complete, then our tokens can go ahead and leave the system. So hopefully pretty simple and straightforward. I would expect this to take probably in the range of 5 to 10 minutes. So take a few minutes to give this a try, and then we'll do a walkthrough and explain a little bit what this tip says about using flowchart containers to help organize our process flow. Sound good?
Let's do it.
All right. If you have any questions, let me know. Since this is going to be a model that incorporates some process flow, I'm going to go ahead and make a general flow. And I'm going to show you guys something here that I recommend as part of the workflow for building a model in process flow, where I'm going to recommend the use of some things in the library that are not activities per se, but they are display aids that are found in the bottom of the library kind of area. And these are what we call containers. We refer to these as flowchart containers. So the idea behind the containers, if you click on the container option in the library, it pops up some different visuals that we can add into the process flow to help organize and add some structure to the flow of your activities. Because one of the things that we try to do with the process flow environment is to make it as documentable as possible, where you can include things like images, text, but also these containers to kind of help tell the story of the flow of the logic that you're putting into a process flow. And you'll notice that they have like the standard kind of flow chart design shapes that you'd see in flow charting programs. And so I like to use these sorts of things as part of my planning process for what I'm doing in process flow. So like before I even do any activities, I might bring things out like this start point, and say that, this might represent the beginning of phase 1. That's good. And then you might bring in like some other of these little blocks and just kind of arrange them in such a way that, again, they help tell the story of what your inspection. Okay, I can spell. Inspection phase 1. They help tell the story of what your flow is going to do. And you can copy and paste in process flow just using standard keyboard shortcuts. Control C and Control V. And like I said, setting this sort of thing up is really about, kind of planning things out. Like I haven't defined what the actual logic is, but I'm putting this flow chart together as a way to kind of help understand like what parts of the model I'm going to need to work on. Like I need to come up with a way to do, to kind of begin phase one, how to do the inspection step in phase one, the painting step, the curing step, and then finally ending. And with the containers, you can also draw connectors between them just as if they were activities. So if you put your cursor again on one of those circles, you can draw a connector to one of these other boxes. Again, just trying to help give a sense of what the flow is going to look like before before you actually start really defining what the behavior is going to be. And like I said, this doesn't affect anything behaviorally about the model yet. It's just a way to kind of give some organization and structure and some planning about how the model is going to work. And like I said, too, the use of these is totally optional. You don't have to. I recommend them. I think that they're really helpful for, kind of helping you know where you're going. When you're building a model, sometimes it's really easy to go down rabbit holes that you don't tend to. But if you kind of structure things out a little bit first and give yourself an idea of what parts of the model you're going to be focusing on, even if you don't end up filling in all these boxes right away, right? It can be helpful for helping just kind of plan things out and help you stay on task, on target for what you're trying to do with your model. Now, these are also containers in the sense that you can take activities from the library and place them inside of the container to help, again, give that sense of structure and organization. And then if you take one of the containers and move them around, right, then the contents of the container go with it. So I'm going to say that this source activity, I'm going to rename it create phase one, phase one tokens. And then I'm going to set my arrival rate to create a token every 30 seconds, just like the description asks for. And then in each of these boxes, I'm going to bring out a delay activity. And the delays here are going to represent the time delays associated with what it takes to do inspection. So here I'm going to say delay. This is going to be my inspection time. Oops. And then I'm going to have another delay. That was the double click menu that we talked about yesterday, by the way.
Regan, actually, can I stop and ask a question?
Sure.
Which menu do you get the shapes, like the oval, the start inspection phase?
Yeah, so in the library, there's a section called container.
Container, okay.
So it's like you'll have to scroll all the way to the bottom past to where it says display is the subheading, right?
Got it.
And then when you click on container, you get all of that.
Got it, I understand, thanks.
Yep. And then finally, another delay to represent the time that it takes to do curing. And then finally, a sync for removing tokens out of the model. So I'm just going to call this, we'll call this sync remove phase one tokens. Okay, so like I said, we're kind of starting to flesh out what the model is going to need to do. But the delay activities by themselves isn't going to be enough, because if I run this, we'll notice that tokens potentially can be processing at those delays in parallel. So that's this first token that's going through, no real issue. But as soon as we get like some other arrivals, you can see occasionally there are other tokens present at the delays being processed at the same time. And that's kind of what we're trying to avoid, right? Because we said at the beginning of the description that there is a resource that needs to be acquired to kind of manage the availability of tokens' ability to do this delay time. So this is where the resource is going to come into play to allow us to use the resource as kind of a gatekeeper on tokens access to these. Sorry, I'm a little bit OCD about like where activities are located. I need to make sure that they're centered.
So then you don't have to connect the activities anymore. They're connected through the containers, right?
Yeah, yeah. You notice that the containers on the connectors on the container pass the tokens from block to block. Yeah. So anything within the container would still need to be linked together somehow. But in order to get the token to go from like this container to this container, I can just use the connector that's between them. Again, trying to lend a little bit of visual context to the model. Okay, so I'm going to bring in my resources. I'm going to create a resource and I'm going to place it over here. And I will call this resource my inspector. And it has a numeric count of 1 because there's only one inspector available. And then I'm going to make another resource. And I'll call this my painter. And again, numeric count of 1, where I only have one painter available. And then associated with curing, I'll have my curing resource. And I'll call it curing base or something like that, because there's actually going to be more than one of these available. We're going to say that the count here is 3, because we can have up to 3 tokens curing at the same time. Now, as far as like how I'm laying this stuff out, this is just, again, the style that I've got accustomed to myself, putting the resources right next to the container blocks where the activities are going to use them. You don't have to do something like that, but I find it useful. Again, trying to allow the layout of the flow help tell the story of what my flow is going to do. But in order to use that resource, I need my accessing activities. I need to acquire. Now, here's a little bit of a problem that I don't like about the way we do this. But I'm going to point it out to you because this can definitely happen. I created each of these resources, and this first acquire that I made assumed that I wanted to link to the most recently created resource. That's not what I want to do. So I'm just going to bring this acquire down to be part of this phase or part of this block, because that's actually the acquire, or rather the resource I want to acquire is right there. So then when I create another acquire activity, this acquire doesn't actually know who it's supposed to connect to. That's why it has the red exclamation point on it. So I can mouse over that to get the eyedropper and then choose the painter. And then I'll also create my release right there. And then I'll have my acquire, associate that with my inspector, and then have my release there. Okay, so kind of imagine that we're mimicking kind of the behavior of a processor, but kind of in the abstract, where a token represents a job that needs to be done, and it needs to use the inspection resource, and then it needs to use the painting resource, and then it needs to use the curing resource. And so the creation of the tokens dictates how often these resources are being requested, and the delay time is indicating how long those resources will be used by a given token.
Good question, Regan.
Yeah.
Why wouldn't you put the resource inside the container?
You absolutely can. It's just this is the style that I've started using because, like, to me anyway, if you put the resource inside the container, it's kind of like saying that the resource is only used here. But as we're going to see a little bit later on when we add additional phases, these resources are actually going to be shared by a lot of blocks of activities like this. And to me, it makes more sense to have them be outside of the containers to kind of show that they are like available to be used by other activities. But again, it's just sort of one of those things that I recommend people kind of develop their own styles about how they want the documentation aspects of process flow to help tell their story. But yeah, you can definitely, you know, put these things in there. So to again help reinforce some of the stuff, I'm going to give you guys another phase that is very similar to the first phase. And the main takeaway from this phase is, again, that shared nature of the resources. So right alongside the current flow of activities that we've made, we're going to make another flow. And it's going to create a separate token that is created at the same rate using the exponential distribution, but it's going to be a separate source. And it's going to create an independent token, independent of the other token that we created that's flowing through our phase one flow. And this token is going to execute a series of delay activities that represent cutting, inspection, and polishing, which need to be done in that order. Now, for cutting, that will require the creation of a new resource with a count of 1. Polishing will require the creation of a new resource also with a count of 1. But we want inspection, the inspection resource, to be shared between phase 1 and phase 2. And then once the polishing step is done, then again the token can leave the simulation. Okay, now one thing as a tip down here, it says copy and paste is a good way to quickly recreate similar activity blocks. Just make sure you double check things like resource links to make sure that the acquire activities that you copy point to the resource that you intend. Because when you copy and paste, all of those kinds of links and relationships are preserved. Okay, any questions there at all? Okay, take a few minutes to work on that. If you have any questions, let me know. And then we'll plan to do another walkthrough in about 10-ish minutes, thereabouts.
On the release function, it defaults to the last acquired. You can select the specific resource that you want it to release, right? I think I heard you say that earlier.
Yeah. What we do is we provide a mechanism through labels where when you acquire a resource, we assign a label to the token. And we haven't talked about labels in process flow yet, but we'll go into a little bit more. But in the acquire activity, we assign this label called resource that keeps track of what was acquired. And then at the release activity, it says that you're going to release whatever was acquired on the label called token.resource, which is a label called resource that is assigned to the token. And so if you have different labels, like we default to resource as the label name, but if you were to have different labels with different names, then that's a really easy way to make sure that you're releasing the right thing by just referencing the right label where the acquire saved the reference to the thing that you acquired. Does that make sense?
Yeah, I guess my question is, when you say last acquired, what if my last thing that I acquired on the simulation was like the cure, but I just, I want to release the painter job, but the last one that I just acquired in all the different sections of acquire, like, is it like the last required, I guess, our last acquired, is that a global? Or is it just like in the section that you're looking at?
Yeah, so it only applies if you have multiple things acquired at the same time. Okay. Right? So like if I were to have like this acquire that is associated with painting, right? If I put that first, that would mean that first we acquire painting, and then we acquire the inspector, and then we do the delay time. And we've got both the inspector and the painter acquired at once. Right?
Yeah, but isn't it possible, based off of the randomness of it, that you could acquire both of them, 2 different things at the same time? Like you build up a queue, like up in the painting, and it just happens to release to curing the same time inspection receives another?
Only if you design it that way, right? There's no way for you to get to this acquire without passing through this acquire, delay, and release first, right? Because of the sequential nature of the events.
I guess what I'm asking is token number 5 and token number 82, could they both be acquired in different sections of the flow at the same time. For example, if we release, token 50 from painting and it gets acquired in curing at the exact same time that the source releases another, token, whatever, the next one in line to the inspection, is that ever a risk?
No, because what I think you might be conflating two things, because you're talking about releasing tokens, and what you I'm not sure if you mean like tokens leaving one activity and going to another.
So they're being acquired at this, like it just seems like it's.
But the tokens aren't the things being acquired. The resource is being acquired by the token. And so if all of the availability of that resource is like occupied by a given token, then it has full control over that resource and no one else can use it until it gets released by that token that's using it, right?
Yeah.
And so
you're acquiring the resource.
Yeah.
Your token.
Yeah.
Okay.
Yeah. The resource is acquired by the token, not the other way around.
Yeah.
Right. So kind of think of it like with like the shared assets. It's like, imagine you have a toolbox full of hammers, right? And you have all of these different jobs that require the use of a hammer. So you go over the toolbox and you get to acquire a hammer, right? And while you have the hammer acquired, you can do your job. And then when your job is done, you got to bring the hammer back and put it in the toolbox. At least that's what I tell my kids, right? So you have that acquired for the duration of the job, and then you put it back. And now it's available for other people to come over the toolbox and say, hey, I need that hammer, right? They acquire it, they go do their thing.
Yeah.
Right. So in that way, you don't have to worry about managing, what if, you've got these two things acquired at once, because that's something that you decide by the sequence, right? And so if you want to have like inspector and painter acquired at the same time, that's okay. It just means that when it's time to release it, you have to think about, okay, when I get to this release, am I releasing everything that I have acquired? Like think of it like a toolbox. You go over the toolbox, you acquire a hammer and a screwdriver, you go do your thing. And then when you come back to the toolbox, are you releasing rather both tools at once? Or are you only putting back the screwdriver and you're going to go do something else with the hammer? Or, is it the other way around? Right. And so that's what the releasing activities are for, is they're figuring out what are we putting back for use by somebody else.
Got it. Thank you.
Yep.
From a resource acquired standpoint, are you able to set priorities or like a max or min of like amount of time for acquiring?
That's a good question. Yeah, there are some different controls that you can have with the shared asset. Like I mentioned, that the shared asset, the resource, manages its own queue by saying that the first unfulfilled request is the next one that I'm going to do. But there are other options that are available with different reference types, where you can set up like a queuing strategy for jobs that are waiting their turn to use the resource, or a query that lets you choose a particular resource with different properties, so that you can define different ways of like managing the queue, essentially, of requests that are being made on a resource. Those are a little bit more advanced options, and those options are actually explained in a walkthrough model that I provided in the download materials. If you look in the set of download stuff that I sent, there is a model called Resource Walkthrough that talks about some of these different like reference types and what the queue strategy does, what the query does, and what the query on the acquire does, and that gives you some additional options for managing like a backlog of requests made on the resource.
Awesome, thank you.
Yeah. Right, so if we do the walkthrough for, actually, yeah, I'll just do the walkthrough really quickly. So the walkthrough for phase 2, it should feel pretty similar to phase 1, and we can do a lot of what we want to do with just copying and pasting. Like if I copy that start point and say, okay, this is now starting phase 2, and just changing names to increase the documentation of exactly what's going on here. So now I'm going to say that I'm going to copy inspection. but that's actually my second step. So I'm just going to put that right in here. And then, you know, like I said too, with copying and pasting, the acquire activity that I copied already knows that it's supposed to acquire the inspector at this point. And so that's fine. But if I were to use that same block of activities as a template for the new cutting step, then I would need to, in addition to changing any documentation that I made, like I'm doing here, saying that this now goes to inspection time, this is now cutting time. But now this acquire is looking at the inspector, but I would need that to be associated with this new resource. And by the way, that was the double click menu again, just like we did in the object environment. We can do that here as well, where we say, this is my resource for my cutter. And this acquire needs to be associated with this resource. So I use the eyedropper on the resource reference of the acquire to make sure that we're pointing at the right thing. And then just my connector there. And then I'll make another block that I'll rename phase 2 for polishing. I need another resource for my polisher. And now this acquire will also need to re-reference that so that we're looking at the right stuff. And then I'll copy my endpoint, put it over here. So you can build it a little bit faster with copy and paste than if you did everything step by step. But there is a little bit more to think about in making sure that like things like these resources are looking at the right thing. And kind of the neat thing about this phase now is that when those tokens are going through their flows, when they reach inspection, they're going to be competing against other tokens in the other flow. In fact, right here, you can see this token is queuing up at the acquire activity in its flow as it waits for its turn to do inspection. Because over here, the resource is in use by this token, and we can follow the red and green lines to see who are the tokens that are making an unfulfilled request and what token is the one that is actually using it. So when that token gets done, then that token is allowed to progress to its activity where it's allowed to own the inspector. So again, highlighting the nature of the shared asset, right? Where you can have tokens in disparate flows in your model, all trying to acquire the same resources, and that's fine, because that is, you know, like we use that toolbox example where we have these tokens that represent jobs that need to be done. They need the inspector, and so they might have to wait their turn as the inspector becomes available as they continue along in their different flows. Any questions there at all?
Yes, sir. Organizationally, you have 2 unique syncs for each phase. Functionally, could you tie the phase 2 polishing to the phase 1 sync?
Sure. Yeah, that'd be fine.
Okay, thanks.
Yeah, the only reason why I'm doing them as separate syncs now is partially for consistency, so the 2 flows look as much the same as they can be. And one thing that we're going to do in the next phase is for statistics outputting reasons, there might be a good reason to use 3 separate syncs. And we'll see that in the next phase. All right, why don't we take a 15-minute break? And when we come back, we will jump into phase 3. Okay, so just to keep drilling into us how to use these process flow activities, we're going to go on to phase 3. And phase 3, a lot like phase 2, is going to be another flow of activities that's going to go right alongside our current model. But this time, our newly created part, our new token, is going to execute delays for cutting, painting, curing, and inspection that are done in that order. So notice here that our new flow is just using the same resources that we've already created, creating additional competition for the use of those resources. And yeah, just continuing on, giving us another kind of part that is competing with the same resource that we've already got. So after inspection is done, that's the end of the flow for that token. And for an output from this model, it might be interesting to try to figure out what is the throughput per hour of each of our 3 different flows. Or if you want to think of them as 3 different part types, that would be another good way to think of it, where we have the phase 1 flow, phase 2 flow, phase 3 flow, and we want to know what the throughput per hour is for those 3 flows. So you could use a dashboard library chart to help with that. And so just take a few minutes to work on phase 3, and then we'll do a walkthrough for that when everyone's had a chance to give it a try. Okay, well, if there are no questions so far, then I'll just quickly do the walkthrough. Again, largely for the benefit of the recording. So in this one, we can put it together a little bit faster because we already have all of the different activity blocks defined that we need. So copy and paste makes this come together in relatively short order. So we can say that we've got, start for phase 3. I'm just updating the documentation as we go, just, so it looks nice. And our first step is cutting. So I'll bring that over here. Don't have to worry about adjusting the properties for the acquire activity because it's already connected to the right resource. I'm just going to change phase 2 to phase 3 though. And then our next step was to do painting. So I'll just grab painting from over here, paste it over there, make our connection, rename this to phase 3. And then our next one is curing. So I'll just go ahead and grab that one as well. Phase 3. And then we just need an inspection. And then we just need to end. So I'll grab an endpoint and I'll make one of those as well. All right, so again, when we start watching this run, we just see the different flows going through their sets of activities, competing with the resources along the way. And pretty simple and straightforward here. Copy and paste helped us out a bunch on this one, and then just using the containers and the activities as a way to kind of help document the environment a little bit, help us give us an idea of what's going on here. Now, as far as the output goes, where we want to know the throughput per hour of each of these 3 flows, we can do that with a dashboard pretty easily. So I'm going to make a dashboard window, bring it over here instead. And in our dashboard, I'm going to create a chart that is for the output per hour. And I'll do this as a bar chart. Now, just like we did with the 3D objects, we can add process flow activities to these charts. So under the object section, rather than using like a 3D object, I'm going to use the eyedropper to select my 3 sync activities. Say that I want to gather the stats from the phase 1 sync, the phase 2 sync, and also the phase 3 sync. And when you run it, then you'll just get a bar for each of those syncs. And this is, again, one of the reasons why it's good to rename the activities to be something a little bit more descriptive, because if I just left them with their default names of sync, it would just say like sync 1, sync 2, sync 3. But if I add a little bit of documentation, that really improves the readability of the charts. And this is also a good reason why you would use potentially 3 syncs instead of just 1. Because it's really easy to gather stats from the individual syncs, at least more so than it is to try and like have a single sync and then differentiate the different tokens based on what flow they went through. I would need a label for that, which you could do, but this makes it a little bit simpler to get these like per flow statistics set up. Okay, anyone have any questions there? Okay. So one thing that's kind of interesting about this model that we've built so far is that this is actually a fairly common problem that that we try to solve in models, or rather a very common kind of logic that we try to recreate, where we kind of colloquially refer to it as the job shop model, where we have multiple different types of products that are all competing for a set of resources in different sequences, where there are various processes that have to be executed, and every one of these different parts uses these different resources in different sequences in different orders. And so this comes up a lot in simulation modeling. And prior to process flow, you would have had to model it in such a way that the flow problem, the flow side of managing this kind of a model, would have to look something like this. Now, obviously, this is a very scaled down version of what we've been doing, but the principle is the same, where you would have these individual stations that all these different parts would need to be able to flow to. And you would have to make a decision after every single station that says, hey, like, for example, if I'm at station 2, then whether or not I go to station 3 or station 4 next depends upon what kind of part I am and where in my sequence I might be, where in my overall flow I might be. And so managing this kind of flow ends up being a little bit more difficult, because you have to kind of know what all of the different available routes are going to be up front, and you have to kind of build the logic to make all of the possible routes work all at once. And that can sometimes be difficult to manage when you're having these like very kind of like spaghetti bowl crisscrossing kinds of flows. But what process flow allowed us to do was allowed us to reimagine this kind of a flow, which is more like a real life type of a flow, into something a little bit more abstract, but functionally equal, where our flow is now described as a set of linear flows that compete for abstract resources. So rather than having to actually cause our tokens to flow to the same block of activities in order to use those resources, we can define sets of activities that are abstract and allow us to acquire a abstract resource, so that we can define each of these 3 flows as a linear flow without the interaction or the worry of how another flow might interfere with the flow of the first flow. And that's why we built the model the way that we did, where we started with phase 1 and said, okay, let's define the flow only for one kind of a part and make sure that it looks the way that we want. And then let's define the flow for a second kind of part that just happens to use the same resource. And then also the flow for a third kind of part that's also competing with those same resources. So rather than having to figure out how the phase 1 flow needs to be able to interact with phases 2 and 3 flows, I can define them more or less independently and just allow them to exist as these linear flows, which is easier to follow for someone to look at this model. They can kind of look at this and say, oh, I see what's going on here. Much more so than looking at something like this and trying to figure out, okay, what kind of thing just went where? Why is it over there? What happens next? Instead, I can visualize it like this and allow the logic to be more comprehensible and also easier to manage. Functionally, these 2 different kinds of flows are equal, but they are just constructed differently so that I can visualize the flow and manage the flow in a less complex way. Rather than having to do it with a series of decisions, I can just do it with a series of linear flows. Does that make sense? Anyone have any questions on that different point of view, that different perspective on the flow? Okay. So again, what we're doing here with this kind of a design is leveraging the abstractness of process flows, so that rather than having to be more concrete or more literal in the way that you interpret a model in the real world to a set of logic in your simulation, you're given a little more flexibility, a little bit more freedom to define a model in a way that, though it may look different logically than real life, like in a physical sense, it gives you the same logical results. And that's a nice way to use abstraction to your advantage to make your models easier to implement and easier to maintain. Okay, now in this next section, we're going to introduce a couple of key ideas. And so the description for phase 4 says that we want to kind of condense the model a little bit, because we do have a little bit of redundancy. And figuring out like how much redundancy in a process flow model is okay and how much you want to get rid of is really kind of a design choice. So we're not going to get rid of all of the redundancy in this model, but we will kind of look at how we might use some capabilities of the software, like being able to make logical decisions and being able to have labels again, can potentially help us slim down the number of activities that we have to condense things to a little bit lesser degree. Now, not so much that we lose some of the comprehensiveness of the model, like maybe we like the fact that we can see these linear flows side by side. So we don't want to necessarily transform this to something that's like super abstract, but to be able to use logical decision-making in the flow where it makes sense, and also to use label values to help us make those logical decisions. So similar to what we saw in the object environment, we can have labels assigned to tokens. And labels in process flow are even more important in my mind than as they are in the object environment. And so rather than having trigger events that allow us to say, hey, when this event happens, assign these labels, instead we have an activity that allows us to assign labels at any point in the flow where you might want. And so similar to the way that we assign labels in the object environment, first you have to establish who the owner of those labels is going to be. So this first edit field on the assign labels activity says that we need to indicate to whom these labels will be assigned. And in this case, it says we're saying that the labels are assigned to the token. And in this case, the keyword token represents the token that causes the assign labels activity to actually happen. So whatever tokens are present here, those are the tokens that are going to be assigned these labels. Now, the interface for this is a little bit different compared to what we saw on the trigger events, where we say that the labels, all of these labels are going to be assigned to this token, and then you establish the name of the label, and then some way that you want the value to be assigned, whether it be by like a percentage or according to a distribution, or maybe even looking that value up from a global table. So let's take a look at an example of doing something like this. So I'm going to come back over to a model. I'm just going to get rid of the model that we were working on. And in a blank process flow, I'm going to create a source. And then right after that, I'm going to say that we will do an assign labels. Now, in this assign labels activity, again, remember that it says we're assigning the labels to the token, and we are giving the label some name and then some value. So let's start with something similar to what it says on the slide. Let's say that we want a label called type. So I'll say this label is named type, and then I need to define a value. So if I were to just type in the number 1, right, that means that everything gets assigned the value of 1. And if we just take a look at what that looks like, every token that gets created, if you click on it, you'll see a label here that says that this token has a type, and that type is the value 1. But if we change the way the value is assigned, we can see there are some other options in here, like using distributions or using a table. In this case, we'll choose by percentage. Now, this is a familiar interface. We saw this on the processor send to port, but we're also using it here where we can assign a percentage associated with a value. So you can do something like this that says, let's say that 40% of the tokens that execute this activity will be assigned a type label that is a value 1. And let's say that we have 35% of the tokens that do this activity that are assigned a type label with a value of 2. And again, since this has to add up to 100%, we'll say that 25% are assigned a value of 3. And again, with the values here, they can be whatever values you want. I'm choosing simple numeric values just because that's fairly typical. But if you wanted to put in text or something like that, you could do that as well. Okay, so this becomes my method for assigning the value. And if we hit reset and run, we will see that these tokens have a type of 1, type of 3, type of 3 again, type of 3 again, type of 2. So all of the types are represented in here because the values for the label called type are just being assigned according to these percentage, this like custom percentage distribution. Okay. Now you could also say that you want to add a second label. Like maybe you have a label here that's called weight to represent the weight of whatever this token represents. And so here you might use a distribution, like maybe you choose something like uniform, where you say that the weight ranges between 10 and 50 units of weight. Call it pounds, grams, kilograms, doesn't really matter. It can mean whatever you want it to mean. It's just a value that gets interpreted by you. So now when you run this, we've got these tokens that have both a type label and a weight label. And so essentially what we're doing is we're creating attributes that indicate how much, or rather that indicate information about these tokens. It represents something with a certain type and a certain weight, and that's being represented here in the labels. Now, the example on the slide also has another interesting example where maybe a label value needs to be found by looking it up from a global table. That's something that we haven't done before, but it's something that's fairly common. So let's take a look at doing that. So let's say that we had a table. So I'll just have a global table, and I'm just going to dock it over here. And let's say that we have 3 rows. And in this table, we have a column called time. Let's say that row 1, we've got 12.75. Row 2, we have 20.13. And in row 3, we'll say that we've got 80.36. The numbers aren't, anything in particular. It's just, show some random numbers, and I want those values to exist in this table. Now, if I wanted these values to be assigned to a label on my token, I could say that we've got another label, and I'll call this label time. And the value will be assigned by doing a global table lookup. And so I want to look at my table called global table 1. The column that I want to look at is column 1, and then I need a way to choose a row. So maybe these 3 rows represent times associated with type 1, type 2, and type 3, rows 1, 2, and 3. That means that in my row, I could use a label that I already created as an input to this edit field. So I could say that I want to use my label called token.type, and that's going to be my way of finding a particular row in a particular column of the table and assign that value to the token. So this is something that we did like a version of that when we were getting those processing times out of the global table in the first modeling example from yesterday. And we're doing something similar here, but rather than choosing a processing time, we are choosing a value that is written to a label on the token. Now, one thing that's kind of cool about this is that process flow keeps track of the labels that we have declared. That means that when I came to this drop-down menu and I looked for something that's to do with a row, it knows that I had labels declared for time, type, and weight, and it gave me the option to choose one of these labels as an input to this property field. That's one of the nice things about process flow and using labels, in my opinion, is that it keeps track of all the labels that we've created, and it more easily allows you to use labels as inputs to activity properties. And we're going to see another example of that in a minute. But does anyone have any questions with what we did so far?
Just formatting, sir. Can you assign colors to tokens in the same way we could objects or
Yes.
flow items?
Yes, and we'll do an example of that in a minute as well.
Thank you.
So if we take a look at what we've got so far, right, again, we hit reset and run. And now we have 3 labels. We have a type, we have a weight, and now we have a time. And each token has a unique set of these label values. And like what was just brought up, right now, if we take a look at these tokens, visually, it's hard to know which one is which, right? Because they all look the same. And it would be nice to be able to add colors to these tokens. Now, there's a couple of different ways that you can apply colors to tokens, like we did with the flow items. One way is pretty unique to process flow, and it's a way that I like to show because it's a really quick way to do this, where if you click on the background for process flow, in the properties panel, you get now a set of properties related to the process flow environment. And under the More Properties button, this brings up a separate window that has some additional options about how to manage your process flow. And under the Visualization tab, we can set different properties related to how the environment actually looks. So there's a number of options here. I'd invite you to explore those sometime, but the ones that we're really concerned with is the section that says token colors. And so the token colors can be assigned from this window by referencing a label that has been created in your process flow environment. So if I go to the drop-down menu that says label name, I can say that I want my token colors to be assigned based on type. And if I hit apply, that automatically changes the color of my tokens, even if they already exist in the model. Now, the reason why I chose type is because type is an integer value. And what the token color section does is it assigns a unique color for every unique value of that label that it sees in the model. So that means we get really simple colors like, green, red, blue. But if I were to choose a different label like weight, it would give me a lot of individual colors. That's kind of hard to differentiate because weight is a real number and it's trying to assign a unique color to each value of weight. And so you're not going to get colors that are the same color. You're not going to get tokens that are the same color that way. So if we use an integer label like type, we get a more distinct set of colors associated with those categorical values for things like type. So anytime that you want to use a label as a way of designating colors, I would make sure that it's an integer so that this mechanism works better. Right. And so now I can look at this and I can see that I have, different color tokens to represent my different types. So I know that all the red tokens are going to be type 1, all the green tokens are going to be type 2, and all the blue tokens are going to be type 3. Okay, any questions on that so far? All right, so now that we have these different label values, what can we do with them? Well, similarly to what we saw with the object-based examples, yesterday and today, we can use this information to cause our model to behave in different ways. And one of the most common ways is to use the value of a label as an input to an activity property. So let's say that I've got a delay activity right here. And normally we let the delay activity define its own delay, like using some value here, like the exponential distribution or some other distribution or a number that indicates this is how long the delay lasts. But again, one of the cool things about labels in process flow is that if we want to, we can use that label as an input to this field. So like, for example, if you go to the drop-down menu associated with this edit field, there is a section that lets you look at your token labels. And if I were to choose my time label, it's going to fill in this expression that says token.time. And that means that whatever value we find in the time label on the token, that's how long our delay time is going to be. So that means if you're a green token, you're going to have a delay of 20.13 seconds. If you're a red token, you're going to have a delay of 12.75 seconds. And if you're a blue token, you're going to have an 80.36 delay time. So I'm just going to send that to another delay after that. But if we reset this model then and run, then we can see that the red tokens have the fastest delay, the blue tokens have the longest delay, and the green tokens have kind of like the medium delay. Because the delay time is being found by looking at the label that's assigned to the token and interpreting that value as a delay. And again, the nice thing about it is that I didn't have to type it because process flow knows what labels I've assigned to my tokens so far. And I can more easily use these kinds of menus as an input to the activity. All right, any questions there so far? Okay. Now, another way that you might use activities, or excuse me, use labels is in conjunction with a decide activity. Now, the decide activity is basically a way to make logical decisions in your flow based on various conditions. Now, before we talk about how to use labels in conjunction with the decide, let's talk a little bit more about why we need an activity like the decide and how this differs from what we've seen in like the object-based the object-based tools. So let's say we have this delay over here, and I'm just going to temporarily delete that connector. And let's say we have another delay over here. And maybe we want a situation where some of our tokens go to delay 1 and some of our tokens go to delay 2, right? Now, normally what you might think is say, well, if I draw a connector over here to delay 1, then some tokens will go there. And if I draw another connector over to delay 2, tokens should go over there as well, right? So if I draw a connector though, notice that the first connector went away. And it doesn't matter how many times I try to draw a connector off of this delay, I can't ever get another connector going to this other delay. Okay, now this is the case for the vast majority of activities in process flow. The vast majority of activities in process flow only allow for a single outbound connection. You can only connect to one other activity. You can't connect to two. Okay, now this is part of the design philosophy of process flow that said we want to keep things simple. Notice that on the properties of the activity, there's nothing in here that is similar to send to port that says how we're going to choose how to use one of our connectors. Because if an activity only allows you to send to one activity, then there's no reason to have anything that says, how do I choose how to send things to another activity? So what we did instead is we put the ability to choose from different connection options in the hands of special activities like decide. The decide activity, if you make it part of a block, it would allow for multiple outbound connections, and it provides a mechanism, a property that allows you to dictate where tokens will be sent to. Okay, so the decide activity is one of our exceptions to the one outbound connector per activity rule and allows you to establish logical decision-making capabilities that say how tokens are going to get sent from the decide to other activities. So rather than have every activity have the ability to make a decision, we created a special activity just for making decisions. And you'll only use it if you need to, rather than having a bunch of logical decisions that get made every single time an activity wants to leave, or rather every single time a token wants to leave an activity. Okay, so the decide activity has a really important property in it called send token to. And this is the way that you will allow your tokens to make decisions about where they're going to get sent to. So it's very similar to send to port on the object side, where if you put in a value like this, that dictates where the token will be sent to. So if you have a number 1 in here, that means that all of the tokens will be sent to the first outbound connector, which is whatever connector was created first. So you can see that if you click on a block of activities, you can see the connectors and what numbers they are. If you click on a connector, it'll just show you what number it is, like that. Now, one nice thing that we can do with connectors, since while we're on the subject here, in process flow, you're actually allowed to give these connectors names. Like, let's say, for example, that the tokens that go to delay 1 should be reserved for tokens that are lightweight. And so I can document what this connector means by giving it some text. And maybe the tokens that go to delay 2 are heavyweight tokens. And so now wherever I move the activity, wherever I move the connector, that text is always going to go with it. Again, to improve the documentation of the flow. And maybe this decide activity, I'm going to say that this is decide by weight. So you're kind of telling a story here that when tokens get here, they're making a decision according to their weight, and they'll either go to the lightweight section or the heavyweight section. So how do you actually make that distinction? How do you decide what it means to be a quote unquote heavy token or light token? Well, this is where the send token to property is going to come into play, where we want to indicate some sort of a logical pattern that says how tokens will interact with this decide. So right now it says everything's going to go to the connector number 1. But if you go to the drop-down menu, you have options that you can choose that allow you to indicate a logical rule for how tokens will be sent to the next activity. So for this example, we're going to choose the option that says conditional decide, because essentially what we want to make is a binary choice. It's either this or this, right? Lightweight versus heavyweight. So if you go into the conditional decide, it offers you a input field where you can make a logical condition statement. Now, normally when we make these kinds of statements, it's going to look something like what it says on the slide, where it says, if token.weight is greater than 35, if that is true, we will do one thing. If it's false, we'll do something else. So these condition fields are usually based on some sort of a comparison of a label against some other value. So for example, here I might say if token.weight, and notice as I start typing, it knows that I'm trying to type weight, and so I can just highlight that and hit return, especially if I'm a bad speller or a bad typer. It's a good help. I can say if token.weight is greater than 35. So maybe if token.weight is greater than 35, that means you're a heavy token. So if this is true, then you should go to the connector associated with heavy tokens. So that means I can either say go to connection number 2, which if you look back on the properties of the decide, you'll see that connector number 2 is associated with heavy things according to my documentation. Or I could even put in the name. I could even put quote heavy token, or not heavy token, sorry, heavy weight. And so the token will look for a connector with the name heavyweight, and it will go to that, that connector. Now, if this comparison is false, then I need to make sure I say, then go to the lightweight, lightweight connector, or just the number 1. I could do that too. So you can either use the name of the connector, or you can use the numeric value of the connector. So if we hit reset and run, then when those tokens get to the decide, they will be split up according to their weight. So if we look at this token, its weight was 11.5. So that definitely failed our condition check where we say, is the weight less than 35? If it is less than that, or excuse me, if it is less than that, then it goes over to the lightweight side. Then over here on the heavyweight side, we have all these heavy tokens. And we should see that their weight values are all 35 or more. Well, no, actually, they should all just be 35. They should just be over 35 because that's how we wrote the condition. We wrote the condition that says only if token.weight is greater than 35. Okay, so that's one example of the kinds of comparisons that we can use in this kind of a conditional statement. Greater than is fine. Less than is fine. You could also use greater than and an equal sign to represent the idea that the weight has to be greater than or equal to 35. You could also do a less than or equal to symbol if it has to be less than or equal to 35. If you use a double equal sign, that allows you to test for equivalence. So that would be saying if token.weight is exactly equal to 35. You could also use an exclamation point, exclamation point equal sign to mean not equal to 35. So all of these different kinds of comparison statements are documented in the manual. If you go to the user manual under the reference section where it says coding in FlexSim, writing logic in FlexSim, and then there's a section that talks about these comparison variables. All of those comparison variables result in either a true or a false statement. And those are the kinds of things that you can put into these condition fields, anything that can be treated as either true or false. And that's one of the ways that the decide activity is very commonly used, where we want to choose this or that. And so again, oftentimes that includes the comparison of a label value against some other value like 35 here to determine whether or not something is heavy and therefore where the token should be sent. Any questions at all? Okay. Now, this is a fine option to use as long as you're making a binary choice, right? Either this or that. But what if you have a decide where we need to make multiple choices, where there's a choice with more than two outcomes, right? So let me make another decide here. And I'm going to say that this decide says that we want to decide, instead of by weight, we're going to say decide by type. Now, remember, back on our assigned labels, we assigned 3 different values potentially to type. We've got a 40% chance to be type 1, 35% to be type, or 35% chance to be type 2, and 25% chance to be type 3. So I can't use the conditional statement that we did for the weight because we have 3 possible outcomes. So then what do? Well, there is another common option that actually shows up in a lot of activities that allows you to make choices based on a case. So there are a lot of options in drop-down menus for input fields into object properties, activity properties that allow you to do something, what we call by case. So the structure of doing something by case means that you can choose one of any number of possible outcomes based on a statement or an expression that has multiple possible values. So a lot of times this means that we're using labels again, where we indicate what's called a case function that has multiple possible outcome values. So in this example on the screenshot where it says case function is token.type, that would mean that we're assuming that token.type has multiple possible values. And then in the case area below, we're defining what possible values of type could be. So you could read this by saying, if token.type is equal to the value 1, then you would do whatever is associated with that case. In this case, it's saying we're going to choose connector number 1. If token.type is equal to 2, then choose connector number 2. If token.type is equal to 3, then choose connector number 3. So the cases are the cases represent explicit potential outcomes of the expression in the case function. So since token.type equals either a 1, a 2, or a 3, we can define outcomes associated with case 1, 2, or 3. And so whatever value we put in here would be the thing that we want to do if the case function equals one of these case values. So that would mean if I come back over to this example, let me just bring connectors into this side. I've got a delay over here and a delay here. And the delay over here. Again, that's just using the double click menu. Then I'll draw my outbound connectors to each of these. I'm going to name these connectors type 1. Oops. Whoops. Type 2. And type 3. Just keep it consistent. Okay, so now on my send token 2, I'm going to say that I want to choose to send my tokens to a connector by case. And so now I have to define my case function. And my case function in this case is going to be to make the decision based on type. So I'm going to look for my type label. And then I want to define what happens if the type label is equal to one of my cases. So if token.type is equal to 1, I want to go to the connector that I've named type 1. And again, keep in mind that everything in Flex in this case sensitive, everything is spelling sensitive. So now I'm going to say if token.type equals 2, then rather than going to some connector that's named connector 2, which I don't have, I can say go to type 2, which I do have. And same thing with 3, where I can say go to the connector that we named type 3. And again, you don't have to use the names of the connectors if you don't want to. You could just use the numeric value, and you can mix and match them if you want. Like here, I'm saying that if your type is 1, then go to the connector named type 1. If your type is 2, go to the connector that is number 2. Right? And so now if I hit reset and run, after I process the tokens by weight at these delays, then I can process them by type by sending them to these delays. And so what I should see is that all the tokens that are the same color are routed to the same delay. Taking a while to get those blue tokens, but now they start showing up because they're slow processors. Hey, any questions at all? Okay, so with the time that we've got left, we'll just backtrack to the description for phase 4. And so what I'd like you to do is to change the model that we've built so far so that rather than having 3 individual sources that create their own independent tokens, we're going to create 1 token every 15 seconds, and then we'll randomly assign that token to go down one of our flows. So we'll use an assign labels activity that assigns a label to the token randomly that tells us what phase it should go down. I said that you should name the label type, but you can really name it wherever you want. The important part is that you have a label, whatever it may be named, that has one of 3 possible values. It'll either be a value 1, 2, or 3, and then we'll use that value in a decide activity to route the token to the correct flow. So if your type value says 1, then you'll be sent to the phase 1 flow. If your type value says 2, you'll be sent to the phase 2 flow. And if your type value is a 3, you'll get sent to the phase 3 flow. So just kind of condensing a little bit, rather than having 3 source activities that are all doing basically the same thing, we're going to condense it down to a single source with an assign labels and a decide to randomly send our tokens to the appropriate flow. And if you want to also assign the tokens a color so that you can visually identify which tokens are going down which flow, that would be a good way to make sure your model is working. Okay, any questions? Okay, now obviously we've only got 10 minutes left, so leave it up to you. If you want to take the 10 minutes and build it, or when you can ask questions while I'm here, that's great. But at 4 o'clock, feel free to go and get on with your day, and then we'll just catch up with the walkthrough first thing tomorrow morning. Sound good?
Sounds good.
All right, good luck.